away.
Hello, everybody. Like Dr. Thorburn just mentioned, this is the Hybrid Personal Mobility Project 83, and this is our final presentation. Our faculty advisor was Del Sharif, Dr. Del Sharif, and our group members was myself, David Canizales, Tony Aders, Darren Sharino, Wersan Al Hadri, Rashid Al Mawar. This is all part of the Department of Mechanical Engineering. Here you can see the picture of each one of us and how we contributed to the design project. There was 4 mechanical engineers and 1 electrical engineer. So like I said, this is just a snapshot of us and how, what kind of work.
David, could you sit a little closer to your microphone, please?
Yes. Is this better?
Yes.
And so as I was saying, this is just a picture so you guys can get an idea of what we look like. And this is, there's 4 mechanical engineers, 1 electrical engineer, and underneath is a description of what each one of us contributed to the design project. We're gonna go over an agenda. So for the introduction, I'm gonna begin that. I'm gonna go over the project background, the scope, deliverables, some calculations, and then I'm gonna hand it over to the rest of the team, and they're gonna go over mechanical design. The frame, brake, suspension, drivetrain will be done by our mechanical engineers, Rashid, Tony, and Darren, and our electrical engineers gonna talk about the electrical design. So for the project background, for many years, the automobile industry has settled for standard sized vehicles, and even considering the size of a compact sized vehicle, which is about 14.5 feet long, is what we consider still reasonably big in order for, or considering the amount of people that live in big cities like Los Angeles. So we decided we wanted to do something about that. The vehicles inevitably congest cities and increase their carbon footprint. As we've seen, there's actually been this is a little bit of a side note, but we've actually seen improvements in our environment ever since the pandemic happened, here especially in the city of Los Angeles. But what we want to do is to continue that and still be able to live in a healthy environment within the cities. So there are some advantages to living in a busy city, right? Because we have so many things that are within a couple miles away. We have the post office, we have grocery stores, we have a lot of things that are conveniently close to us. So we decided was we can create something smaller for people to get around. We don't need to be driving a 14.5 or like a large vehicle in order for us to go run errands or things like that. So we decided we wanted to focus on something like this. This will reduce the congestion, the pollution, and inspire more effective ways, hopefully, for people to create ideas to make us similar vehicles for us to be able to get around. So the purpose of this was to improve the standard of city life while protecting the environment. The project scope for the PDM, the personal mobility device, was that we wanted to make something that was about 1/10 the average weight of a car and size of the average car. So this we're looking at about a 300-pound vehicle, considering the weight of the passenger, the load, and the vehicle itself. And we wanted it to be energy efficient and cost effective. Because we've seen that vehicles can be expensive, the starting price for a new car, for example, is about $15,000. We wanted to reduce that cost considerably. We wanted the total speed to be around 20 to 25 miles per hour to keep it within a safe travel speed. And we wanted to create a hybrid between mechanical power from the user and electrical power from the motor and solar panels. Within one thing that we really wanted to focus on was to keep it within state regulations, because if we were to mass produce a vehicle like this, the last thing we want is to have to change features later that we would have to in order for it to fit city limits or city street limits. So we wanted to keep it essentially as close as we could maybe to a bicycle, so that we can still use it out and not have to worry about breaking the law. The project components for this design are the calculations, the frame, the power source controller, the steering and suspension, pedal assist, and the electrical powertrain. Some of the deliverables and milestones that we're able to complete, we actually were able to essentially complete everything. The only thing that we unfortunately weren't able to finish designing and was left at the suspension, which was the most exciting part. since the suspension is one of the most complicated aspects or parts of the car, we were able to complete it, and we had essentially built everything. All we needed to do was weld, and that's when the pandemic hit, and we were forced to stop working on the vehicle, unfortunately. But we did get enough done in order for us to give us enough experience and to be able to share this presentation with you. Some of the energy calculations for the Powers motor is that we wanted to make sure that they had enough power in order for us to get it to accelerate reasonably well, and also get us to travel a reasonable distance. Without pedal assist, we were looking at 15.6 miles, which is already pretty well, considering we're using a 1 kilowatt-hour battery. And if we consider that an average speed of 7 miles per hour, or 7 meters per second, which is about 15 miles per hour, this is considering a flat surface, no pedal assist, and 60-minute drive.
David,
Yes.
some people are having some difficulty hearing you. You try just positioning yourself differently in front of your microphone, because we heard you better earlier.
Is this better? Here? I'll try and speak louder.
That works better for me.
Okay, so using the pedal assist, however, would give us an additional 32,000 meters, which would be, and if we were to look at it in terms of miles, it would increase from 15.6 miles to about 20 miles. For the power and velocity, we understand that as we increase velocity, the air resistance is gonna increase exponentially. So we went ahead and graphed this to have an idea and to get the best possible, the most reasonable or efficient speed without having to overpower the vehicle in order for us to maybe go 1 or 2 miles per hour extra. And if you guys can see, this is the velocity to power graph. And once you hit, sorry about that, you must have, oh wow, I don't know what. Give me 1 second, I'm not sure what happened. I spoiled it. So this is the graph on how much power we wanted to stay, and we decided we wanted to stay within 2,000 watts for the motor in order, or below 2,000 watts in order for us to get the most efficiency. After conceptual designs and a lot of FEA work, finite element analysis, we decided to stick with this design here. Next up, I'm gonna have Rashid Almarwan take over the frame and brakes.
Hi everyone. Should I share my screen?
Yes, Rashid, please do.
One moment. Can you see the full screen?
Oh, no, Rashid, we see your PowerPoint, the whole frame. You need to put it in the screen mode.
Yeah. What about now?
No. I still see the PowerPoint presentation. It looks like you're still in the editing mode.
Yeah, I tried to enable the slideshow, but shows.
Hit enable editing up at the top. There you go. Yep.
Oh, 1 second.
There's just a delay, maybe.
Oh, okay.
Put it back in screen mode, please.
Is it better now?
Yes. Well, no. Okay. I think what we're going to have to do, I apologize, everybody. We're trying to work out this transcription process. Rashid, I think this isn't working. So maybe we can go back to David driving the screen and
Okay.
each of you can just speak to your own charts. So David, if you would take over the screen again, please. Okay. And let's,
So everybody see that?
yes, we're on your agenda page at this moment. Yeah. Okay.
So hi everyone, I am Rashid. I'm gonna talk about the frame and brake system. For the frame, we thought and we think we study about the first for the safety for the driver, and since it is the main component of the vehicle, so after some research, like we did a lot of research about which best steel that you use for our project. So we found out that chromoly steel and mild steel 1018 that is the best for using, or the common one that we use in the market on the vehicles in general because of the cost and the weight and the availability. So since Dr. Sharif provide us with mild steel 1018, so we use that since we have it, so we save the cost and save the budget. So you can see on the screen that this is the frame that we made so far. It's only missing the cage, that's the top part. And the other part was like the other part just to put it in it. So it was almost, the frame was almost done. Just the cage part was missing. And from the FEA or finite element method, that's originally our weight is like the frame itself is supposed to be 80 pounds. And with all the parts together, it's supposed to have almost 400 pounds. With in the next slide, yeah, in the next slide, so we have some options like for the brake system to use it with this kind of vehicle. So we thought about the drum disc, but it's not gonna work, or it's not gonna be more safe to the driver, since the disc brake is better than any type of brake, since can handle the wet weather, like if it is raining um, or if it is like cold or in snow. And since we are using we decided to use the steering bar, so we use this kind of brake, like we use the calipers on the same steering bars, like easier for the driver to handle it and use it. And also this type is easy to maintenance, and also cheap to buy and easy to find in the market. And, and let's go to the next slide. David? Yeah. So now I will hand the slide to my colleague Tony, talk about suspension. Thank you.
Huh?
Should I share my screen or should David continue?
Tony, try sharing your screen.
Try sharing your screen.
My internet became unstable.
Okay. Can you see?
Yes.
Okay. So this was pretty much my portion of the project. So our team wanted to implement some type of suspension system into our vehicle, since this was going to be like a alternative to like traditional cars. Then our vehicle should have a similar ride and feel to like traditional cars. So we decided to go with a double wishbone suspension. Some of the considerations that we had to include in our design was like the kingpin inclination, the caster angle, and Ackerman steering. So pretty much the most difficult part of designing the suspension was getting the components that we purchased online and like convert them to a digital copy so we could put them in our assembly. Since like we purchased these components from like eBay, Amazon, there wasn't like CAD files available for us to just get and just put into our assembly. So pretty much what I had to do is take some calipers and take dimensions of every single part and try to draw them as accurately as I could. So we used these rod ends for the steering, and this gold and black was the ball joint for the control arms, and this was the shock absorber that we were going to use, which is here. So other considerations that we have to assume pretty much was that the suspension geometry was going to be approximate for the same reasons that I told you before, that the components that we purchased and I drew were only approximations, because they're only as good as the measurements I took and the drawings that I could make. And like Rashid was mentioning, we decided to go for a steering rod instead of like a rack and pinion, which would make the assembly more complicated. So it was just these simple linkages that we would just rotate and we could achieve steering that way. And yeah, that's pretty much for this slide. So I guess the most important part of the suspension is the kingpin, which is this part, which is where the wheel would attach to, and the lower control arm and the upper control arm would attach to as well, and the shock absorber. So the caster angle that we chose to have for our wheel was 7 degrees, and our kingpin inclination was 12.6. And that's just pretty much saying that, like, if we draw lines from the ball joints, that'll just be this angle with respect to a normal line. And this gold, the kingpin, was just me messing around in CAD, which I used some feature called topology optimization, which pretty much just optimizes the geometry of this part. So I would tell it where would it be constrained and what loads would it have to bear, and the computer will like solve this. I don't know, I guess this program, and it will give me the best geometry that could sustain that load. I don't know, it was kind of fun. And finally, for our geometry, we wanted to include the roll center and the center of gravity. So pretty much that's done by drawing lines from the center of the wheel, and it will have to intercept the control arms. So if, for example, if for the right side, if we draw this line all the way out, it would create a point here. And for the upper control arm, if we draw another line, this is pretty much this point out here to my left where my mouse is, that's the instant center. So if we draw a line from that point to the center of this wheel, and we do the same thing for the other side, wherever these lines intercept, that's going to be our roll center. And for our vehicle, it was about 7 inches above the ground, which is okay. I really don't have anything to compare it to, but I guess it was the best that we could do. And yeah, that concludes my part. I'm going to hand it over to Darren for the drivetrain and steering. Should he share his part now?
Yes, please try.
Okay.
Sharing mine right now. It says I have to quit Zoom to give You have to quit. Zoom US will not be able to record the contents of your screen until it's quit. Because I have to give it permission.
Okay.
I don't know what to do.
Perhaps, Tony, why don't you flip the charts
Okay.
while
Yeah, just Tony could do it.
yeah.
Okay. So, hi, I'm Darren. I'm going over the powertrain and pedal assisting and the whole steering mechanism. So basically this picture right here shows the majority of what we have completed thus far, like in real life constructing the vehicle. We made the whole frame, which took a few weeks, and oh wait, Tony, the
Sorry.
screen's kind of messed up. I don't know. So basically this is what we have completed so far, which was the frame. We mounted the motor. We put brackets to mount the motor on. We bolted
Tony,
the
you've
motor.
got your, I'm sorry, you've got that looks like you've got either the chat room or the participants. Just close that.
Yeah, minimize that.
There, well, that's better. At least it's tiny, yeah.
Cool. So yeah, we basically mounted the motor. I made the rear sprocket. I machined that. As you could see, the big black sprocket, it's mounted to the hub. So I basically made a big aluminum clamp to clamp that to the hub, so we don't have to, you know, weld anything to the. We don't have to. We're not able to weld the sprocket to the rear wheel just because they're dissimilar metals. So we had to just basically make a rear hub adapter, and also we could we're able to true up the that big rear sprocket. So going to that the big rear sprocket basically is driven by the motor, and the sprocket on the other side is kind of hard to see. It's a lighter gray. That one just came with the wheel. It's just from the mountain bike, the donor bike that we had. So essentially we didn't get this far, but we were just going to mount the chain. The chain's mounted to the big rear sprocket, and on the other sprocket that we were gonna have a really long chain and weld some chain guides and stuff all the way to the front to where you could pedal from. And we were just gonna use the biggest gear, since we don't want to use a derailleur on the back and stuff. And that would have that big gear would have the least amount of torque, but the highest amount of top speed, since the motor is just to kind of assist, and pedaling is going to be used for once the vehicle gets up to speed, and you're just helping maintain the inertia of the vehicle. So that motor is a 1800 watt electrical motor, was given to us by our advisor, Dr. Sharif, and it came with the controller and stuff. It was pretty nice. We got it working. We got the rear wheel spinning on its own. This motor was used to assist with, you know, hills, because it would be pretty hard to pedal this up a hill, and also starting the vehicle from a stop. Whenever you have to stop, this would help you get the vehicle going, and you're going to be real excellent. So yeah, basically that's what our design was for the rear. We couldn't make it we couldn't make it front wheel drive by pedaling, just because that would be a whole senior project of its own. We would have to have CV axles and stuff, because the front suspension articulates as well as steers, and we can't take that away, because then, you know, it wouldn't really work. So moving on to the next slide. There we go. Okay, so this is basically the front of the vehicle. So that whole pedal assembly was also taken from a donor bicycle. We were going to mount it just how that was. We attempted to, but we kind of messed up. Can't get everything the first try, but it does have a weird geometry to it. So basically we were going to mount the seat in first, which we didn't really get to either, and then mount this accordingly to wherever your legs lined up. So again, the pedaling is just used for maintaining the momentum and inertia of the vehicle. And also, since you have a freewheel gear on the rear hub, these pedals won't be spinning and hitting you whenever you stop pedaling and let off if you're just coasting to a stop, or if you get tired and just want the motor to, do all the work for you. Again, we tried to implement both of those together, where you could pedal and where you could pedal and have the motor working at the same time to, reach a faster speed. But however, if that rear hub is spinning really fast, and your ability to pedal, you will not, you won't be able to pedal. If you're not able to pedal the rear hub faster than it's spinning, you won't be really contributing to any work of moving the vehicle forward. So, and yeah, next slide. And then as for the steering, this is the very first picture I ever found of like a go-kart, like a example, just a go-kart steering, how they did it. This just looks like someone made this in the garage, but it's a really good design because it's very simple, very cheap. Those rod ends were like, I think like $3 or $4 each. So we can make this cheap, really cheap. However, that's the ideal design. However, it sticks up, and if we have the pedals there, it might not work. So our design on the right is what we came up with. We found another example to kind of go off of, and Tony translated that into CAD. And instead of a steering wheel, we have that bar. It's kind of weird in this picture, but it's that horizontal gray bar there. It looks like a piece of the frame, but it's not. Yeah, right there. And that was gonna help with the steering. We bought some 3/4 inch aluminum. I was just gonna cut it off and square it up in the lathe and use the rod ends and thread them in, but we didn't get that far. But it all works in CAD, so it's there. And that's pretty much it. Next slide. And now I'll be transferring this over to Wedgedon to go over the electrical components of this.
Wedgedon, you're muted.
Yeah, hi everyone. Sorry, I was talking. I'm Wajdal Harbi. I will talk about the solar panel. Like you see in the block diagram, it shows the solar panel. It will charge the control, then the battery, the control, then the motor. So the solar panel regulator, also known as the charge, the control assist battery charge, also control the voltage direction of the current and prevent overcharging. In addition, the solar panel load can be connected directly to the battery. We're planning to put the solar panel in the back of the car and in the roof. And because what's happened in our situation, we couldn't order the solar panel for our vehicle. So next slide. And for the battery, we have lithium-ion battery with 48 volts, 2000 watts. And next. So Tony, this one. So we thank for Dr. Adil Sharif and Professor Bachman and Mike for everything. So if you have any question, you can ask us.
Okay, thanks everybody. It was a very interesting presentation. I saw that vehicle in the hallway, well, several weeks back now. I'm sorry to see that you weren't able to finish it. But it's a good project. The and I want to apologize to the audience. We were trying to work out how to do the transcription automatically. That experiment didn't work very well, so unfortunately, this team bore the brunt of that. But in the end, I think the presentation came across. At this time, we have some time for questions. All you need to do is to unmute your microphone and then just ask the question. Who would like to go first? Then I'll go first. If we could go back to a slide that showed the rear wheel assembly and the
one I did.
one toward the, yeah, I think any one of them will be okay. Yeah, that's a good one, for example. It looks like there's not a lot of clearance between the tire and the frame and the seat. How much clearance is there?
It's very close to the frame, but it's all mounted up, like I said, and it spins freely, and we turn on the motor and spun it.
Does it change under weight or loading and anything?
The rear tire will squish a little bit, but not much.
Okay.
Yeah, I think it just squished when we were installing the wheel, but after it was installed, there was about like, I want to say ½ an inch in the front and in the back of the wheel. So I think there was plenty enough of clearance for that.
Okay.
There was just the interference when we were pushing the wheel down, it would hit this frame member here. But inside here, there's like an arc, and there's room here, here, and here. There was like about ½ inch for.
Yeah, so the widest part of the wheel is between those two.
Yeah, so it sticks
Those
out.
two
It like
parts.
sticks out right here.
And we did consider using a smaller wheel. However, Dr. Sharif had this wheel available, so we decided to use this wheel. I believe it was a 24-inch. There are also a lot of 22-inch wheels for bikes that we could have used also. But since we had access to this one, we decided to build the sprocket and everything around this model, and this is the model that we drew up. But we did consider using a smaller one, but again didn't, because this is what we were able to work with.
Okay, thank you. Other questions?
So team, I really give you a lot of credit for learning. There's a lot, these vehicles, there's a lot going on, and you guys learned a lot this year. So nice job on that. And you guys were full steam ahead all year, I could tell, in the makerspace. So I was very impressed with that. One kind of question I have, just thinking about it, if we continue this in the future. So you chose to do 3 wheels, which is not necessarily the most stable setup you could have picked. Do you have any idea what type of lateral accelerations, like how quickly can you turn in this thing before the thing rolls over? Especially with a lot of weight in the back, with the solar panels and the person all over this rear wheel, and unable to transfer any weight in the rear at all. So I'd be curious what you think about that, and maybe in the future, would you think to maybe have 2 wheels in the back?
We didn't really consider how fast you could take a corner with it. It's not really a race car, but we tried to keep all the weight in the middle, and also more or less a 50-50 weight distribution, because that's more ideal. But we considered the roll center of it. It's on one of the slides.
Yeah.
Tony could.
We could talk a lot about roll centers too, if you guys.
Yeah.
But yeah, it's not really a function of it's not really a strong function of your roll center, whether or not you're going to roll over or not. It has more to do with your track width of your vehicle and the height of your CG. But I mean, I think you guys, this is a crazy kinematics problem, a million things going on. So I mean, yep. I commend you guys. Like, for example, you weren't sure where your roll center should be, right? I mean, I guess the question would be, do you want it to be higher or do you want it to be lower, right? Are you thinking about pushing it towards your CG, or are you thinking about pushing it towards the ground? What are the trade-offs there? But that's a pretty complicated, I mean, you feel free to answer, but it's a pretty complicated kinematics question.
Yeah, we really didn't consider, I mean, after we spoke to Blake, he was the one who first like told us, oh, we should probably include like have a roll center in your vehicle to present. But I mean, as far as like having the roll center closer to the center of gravity, the thing that we were considering the most was that the roll center wouldn't be below the ground. And that was pretty much the only consideration that we took.
Yeah, we just didn't want it messed up, like completely messed up.
Yeah.
And maybe, I don't know, for the future, because you know how the rear wheel is like, it's fixed, right? So maybe adding like a suspension in that wheel, I don't know if that would help. But I don't, like as far as going 4 wheels, we didn't even consider that. But I don't know, maybe it's worth thinking about.
No,
Or we
very
could
good.
use a smaller wheel, which would lower your center of gravity, and that would be very beneficial. Because what did David say? The other common wheel size is a 22, so we're using a 26, I think.
Yeah.
So that would lower the vehicle 3 inches or 2 inches.
Very cool. Very cool. Thank you, team. Yeah, it's really impressed with your work throughout the year. What I saw.
Yeah, just fabricating this was was a lot of, yeah, every angle on that frame is different. There's, like 55.2 degree angle that we had to set up in the mill. It was just making the frame took forever.
Yeah.
Are there other questions? Okay, well, if not, thank you, team. It was a good job. I appreciate the presentation. I apologize for the technical difficulties here. So,
Thank you.
okay.
Thank you, Professor.
Okay, up next is the biaxial tension equipment team. That presentation will start at, I guess it could start at any time, actually. I guess we're running on a little bit late. So whenever you're ready, then we can pick up.
Yeah.
Are you ready to go?
Yeah, give me 1 second. All right, hello everybody. My name is Zoheb and we're going to be doing our presentation, which is the biaxial tension equipment. My team members are Onyx, Geraldine, and Eileen, as well as I. And our faculty and Leonze is Drs. Matthew Brew. So for our agenda, we're going to be breaking it up in parts, and I'm going to be going over the project background, the criteria and timeline. So as highlighted right here, I'm going to be going over this, and then afterwards, I'm going to be giving it to Onyx. Okay, for our project background, what is a biaxial tension test? Well, the biaxial tension test measures the mechanical properties in multiple directions, and it provides data on stress-strain relation biaxially with respect to displacement. So what is the importance of biaxial testing? Biological soft tissue tend to have an anisotropic behavior, where each axis has different mechanical properties, therefore making it a dynamic structure. Understanding the dynamic structure of the soft tissue will help us understand, use the data to better mimic the biological properties. So on the right side, I'm going to be showing you what's the difference between uniaxial and biaxial. So the difference is, since the tissue are anisotropic, experiencing loads in different directions, uniaxial testing fails to incorporate the multi-axial characteristics of the tissue. Since we are making a biaxial test, we can better understand the multi-axial loads. Next slide. Okay, for our project background, what is a biaxial tension equipment? A biaxial tension equipment is a machine that will measure the forces of a given object in 2 actual environments. So through mechanical and electrical engineering, this will allow us to achieve precise mechanical behavior and of the biological tissue under multi-axial loadings. And on the left, you can see existing equipment in the market right now. So how the market stands They have the biaxial tension and they have 4 motors and stuff. This is what's existing in the industry. And we're gonna do our own take on it. So here's our criteria for our project. We have to test the mechanical behaviors of biological soft tissue precisely. We have to have the ability to stretch up to 10 centimeters on each axis, ability to pull at a speed less than 1 millimeter per second. As well, to read 0.1 Newton up to 500 Newtons of force, calculate displacement velocity, perform tests under saline solution, and we have to store this in a research laboratory. So in our timeline, you can see what we have scheduled from January till April. January and February went smoothly according to schedule, but in March we had some discrepancies. As the CAD design was approved, unfortunately, we received the parts to assemble the machine the same week as the stay-at-home orders arrived. Since this happened, we were not able to machine the parts. Although we tested both load cells and cameras individually, we were not able to make test runs with the tissue altogether. Therefore, we could not assemble the system as well. And scheduled in April was to debug the system and perform sample tests and finally show in our presentation all the results. So now I'm going to be handing it over to Onyx, and he's going to be talking about the system overview and the overall design with all the parts of the system. Onyx.
Thank you, Zoheb, and good afternoon, everyone. I'll be going over the overall design. Our overall design is 1 meter by 1 meter, which is a very convenient size to store in a laboratory. There's 6 major components in there: 4 mechanical arms, 4 linear rails, 4 brushless DC motors with gearboxes and controllers, 4 3D printed grips, and 1 area scan camera. We also have adjustable camera stand. We have polycarbonate saline tub where the testing will take place. Our all electronics will be attached on an aluminum optical breadboard platform, and it will be very easy to assemble or disassemble all the electronics. To the next slide, we have our mechanical arm, which is custom designed for linear rail platform. It holds load cell and grip. One end will be screwed with the linear rail, and the other end will go into the tub and pull the sample while it's attached with the grip. To the next slide, it's a very simple construction. The arm is 6 inches tall and almost a foot long. It's only 1.5 pounds in weight, and it's very easy to machine. Only metal cutting is involved into machining, and our screws are kept in metric measurements just to be consistent with our linear rail and the load cell. We keep our tool consistent because in case of future replacement or repair, it will be very easy for a technician to have one set of screws. On the other side, we have selected aluminum 606 metal to design our arm because of its strength, of the availability in the market. It's very lightweight and it's very popular in the machining. We are very concerned about the displacement in the arm while it experiences a load from the sample, because it will affect the reading of our camera. The camera will be at a fixed position during the test. So if there is a significant displacement in any axes, we'll have errors in our data. So we ran a simulation on our arm, applying the maximum force we can achieve, which is 100 pounds, which is close to 445 Newton. And the maximum displacement that might occur is in y-axis, which is 0.6 millimeter, if and only if we get the maximum load on it. So we can always expect a lower load or a lower displacement on any axes. The value is very considerable and the effect will be negligible. So we have approved the arm design for equipment. To the next slide, this is a 3D printed grip and it will be attached with the load cell. We have adopted our existing design for the grip, and this grip is also used in uniaxial test, which is very common in the industry. The dimensions are not specified because it can vary with respect to the size of the sample. We were unable to test the performance of the grip due to the pandemic, and also any kind of design modification are necessary according to the sample we get. To the next slide, I'll go over the linear motion system. The linear rail. So linear rail is one of the major components we have. Linear rail converts rotational motion from motor to linear displacement. We needed a linear rail with a stroke length of 100 millimeter, which can carry up to 500 Newton load. Low friction guidance was one of our priority while selecting the linear rail system. To the next slide, this is our tread study, like how we have selected all of our components, especially the major components we have. And we have selected Thomson Linear N50 series among many alternatives we have in the market. If you look at the comparison, the red box represents that it doesn't meet our minimum requirement. The yellow boxes represents that it satisfies our minimum requirement, and the green shaded boxes are they represent that they're higher than our minimum expectations. So we have chosen Thomson M50 based on its capacity to carry load, its higher repeatability, the mounting option, and the lifetime, obviously. To the next slide, we have the motors, and we needed a motor which is compatible with your linear rail system, which generates enough power to support our experiment, and which is easy to control and programmable using Arduino and Simulink. We have selected Anaheim's brushless DC motor based on its power, torque, efficiency, and its lead time. Since Anaheim Automation is a local distributor, so they can always help us instantly and locally whenever we need a repair or any kind of a replacement. To the next slide, it's our same comparison as we have done for our linear rail system, and we have chosen the brushless DC motor based on its power, torque, and the lifetime. We have chosen brushless DC motor over stepper motor because it generates higher torque at lower speed, it has a longer lifetime, it has better positioning, and the outrunner configuration has better ventilation and eliminates noise and vibration. To the next slide. After testing our motor, we achieved our desired speed and power, but it was running at its higher capacity. So we have decided to include a gearbox into our system. The gearbox was not initially included, but regardless of its size, weight, and cost, we decided to have a gearbox into our system. The integration of gearbox will provide accurate RPM and power. According to our calculation, any gear ratio between 64 to 180 should serve our purpose. Selecting and validating of the gearbox is necessary in future because we have just run our simple calculation, but we're not able to pick the exact gear ratio and try to test it with our system. To the next slide, this is the overall view of our linear motion assembly. So our motor will be mounted to the gearbox, and it will be mounted to the linear rail system. And if you look at the top, there's a platform for arm. Our arm will be screwed with it, and our load cell will be attached to the other end of the arm using a screw adapter, and the grip will be attached with the load cell in the same manner. Now I'll hand over to my teammate Eileen, who is an electric engineer, to describe the wiring diagram.
Okay. Hello everyone, I'm Eileen. So before any assembly should take place, we need to be able to connect our motor to the speed control to be able to control it using different approaches. So the diagrams are straightforward connections between the motor and the speed controller, which is an easy process since they are both from Anaheim Automation Company. We did have to buy a separate power supply for the speed controller because it needs about 10 to 12 volts to run. The instructions are below for the connections for this power supply as well. So on this slide, the diagrams below show the voltage verification using a digital multimeter that our speed controller is being supplied a sufficient amount of voltage, which is about 11.56 volts. So on this slide, we have our motor connection. So on the left column shows the detailed instructions on manual mode, meaning that the connections were made only between the motor, speed controller, and the power supply. It is important that it is in internal mode, and the detailed instructions are below on the left column. This step was necessary to do because we need to verify that the motor runs and functions before we can connect it with a microcontroller. So now on the right column, sorry, go back, yeah. So in the right column shows that the detailed instruction on internal mode when connected to an Arduino. So the table below are the connections between Arduino and the speed control. The dip switch setting are also included. So on this slide, we have the motor control using Simulink. So we used the Simulink initially for a speed command because we wanted to see a real-time response when the speed is varied. But ideally, our advisor actually needed to control our whole system using only one software in LabVIEW, which I will show in a future slide. So now I will be talking about load cells. So as mentioned earlier, there will be 4 load cells installed to each grip on the linear rail system. The selected load cell fulfills the requirement of maximum load of 100 pounds, which is about 445 Newton. The load cell has a rating of IP68, which means that it is waterproof and can be submerged for up to 1 meter for about 30 minutes. The table below shows the load cell selection process. The important criteria that led to the selection process was the accuracy, size, and the ingress protection rating. As you all can see, the Flintech load cell wins over the Omega load cell due to its IP68 rating and the smaller in size, which is actually important due to the limited space of our whole system. So on this slide, what you see here is a basic LabVIEW model trial just to test and verify that the load cell given to us is functioning. The graph was obtained by varying the force applied to the load cell using my hands and by connecting it through the DAC system. Okay, so as I mentioned earlier, this diagram shows our whole system in a LabVIEW file. The picture below is the system control panel in LabVIEW. We didn't include the LabVIEW black diagrams, but basically we used the links function to connect Arduino into LabVIEW, and by using the DAC assist function block as well to put the load cells. So for this overview, the system for LabVIEW, we wanted to be able to control our whole system just by using one. That means we can collect data for force, the speed of the motor, as well as we can also get images for our displacement, which will now be talked about by Geraldine.
Geraldine, you're
Sorry.
muted.
Okay. Good afternoon, everybody. My name is Geraldine. I'm going to be going over the image analysis and everything that had to do with our camera module. I'll also be going over the up-to-date costs, our conclusion, and also whatever future progress that we have to make. Sorry. To start off, I'll be going over the camera that we decided to choose. So because of the fact that the skin is, the muscle is very small in size, we have to choose a very precise camera. So we decided to choose this camera because of the resolution. The resolution is extremely high, which makes it so we can see a very accurate depiction of every single sample we test. Also, the frame rate is 203 frames per second. This ensures that there is a smooth transition between frame to frame as we are conducting each test. Also, for the primary working distance of this camera, it's about 165 millimeters, which is about 6.5 inches. We decided to choose this because it allows us to have a more compact design rather than having something that requires a camera from being a further distance. We use this in order to make sure that our system still is able to be stored within a lab setting. This is just a quick overview of the image analysis that could be done with the camera. If you could see on the bottom left corner, that is a sample specimen that we used to test our camera. Because we weren't able to get actual human tissue to use for testing, what we went ahead and did is we used a piece of paper that has 4 dots on it, and we would place it in front of the camera, and we would further the distance away from the camera in order to simulate some sort of displacement. And if you could see on the LabVIEW program that I created, basically what it does is it gathers the images through the tests. It converts it into a black and white image in order to be able to test the point, to detect the points of interest a lot easier. And then from there, it projects a displacement graph that does it through real time. And it's also already calibrated in order to be with virtual axis, virtual X and Y axis and real time. And just to go over the project expenses that we made up to date, we spent a good amount of money for this equipment, but it is a lot cheaper than what is already out. So for the sensor system, we spent around $4,000. The linear motion system around $2,000. The entire image analysis was around $900. Assembly, which includes about the 3D printers that we used in order to potentially make the grip designs, was around $400. The power supply was about $80. So in the end, we spent roughly about $8,500. And of course, we want to give credit to CalCLA and of course, Dr. Briu for providing everything to make this equipment. In conclusion, we were able to get semi-control of the linear rail and also the motor through Simulink, also the functionality of the load cell, and we were also able to test our image analysis. Unfortunately, due to the unforeseen events of COVID, we weren't able to entirely put the system together physically. We were able to simulate everything, but unfortunately, we weren't able to put everything together at the end. So for future things that need to be done by the next following team would be to design a proper grip design for our equipment and also properly integrate the 4 sensors and make sure that they do work hand in hand with all the components of our system. Also, we still need to machine the arm completely together, which we weren't able to do, and also to do the full assembly of the system, and also to get the gearbox to work properly with the linear rail and also the motor. And we also need to be able to test actual samples of biological tissue, which we weren't able to do. And also after we are, the next team is able to conduct all of those future progresses, LabVIEW needs to be integrated hand in hand with both the motor, load cell, and also the image analysis. We wanted to be able to make it so everything is run through one LabVIEW program in order to get every single data into just one file. That way we don't need to extract it in multiple different ways. It could just go onto one file and all analysis will be done at real time.
I'd like to acknowledge Dr. Matthias Briu for the overall support, for sponsoring our project, to be with us for every kind of question and problems we face, and for allocating us space in the school to work together as a team. I'd like to thank Dr. Michael Torberm and Dr. Bachman for hosting the Capstone Senior Design. I also like to acknowledge Micah, who is a mechanical engineering student, and she shared the grip design that she had. And thank you very much, everyone, for being to be present in our presentation. And if you have any question, we would love to answer. Thank you.
Okay, thank you, team. Very interesting presentation. We have plenty of time for some questions. Who would like to go first? Oops. You need to unmute your microphones.
Can I start asking a question first?
Sure.
Sure.
This is a testing bed that is, doing some tests, I'm sure. But Do you have any like safety, excuse me, safety features like emergency shut-off buttons or some kind of limiting switch for the traveling? All those safety, because the test equipment always requires some kind of safety features. Have you considered those features? When you
Yes,
design it?
so our linear rail system comes with a limit switch on itself with the model.
Mhm.
And it's so that one we have in our mind, and we literally have it into consideration as well. For the motors, we have individual motor controllers and we have individual power supply, and that will avoid any kind of like power outage or overpowering the motor.
Other questions?
I have a question, team. So do you, you might have said this and I just missed it. Do you plan to test human tissue in this, or is it mostly going to be tissue that mimics human tissue? And if it is human tissue, was there some consideration for kind of cleaning it, and how would the materials be compatible with typical clean human tissue?
So we consider we can test any kind of biological tissue in it. It's not necessarily human tissue, but human tissue is one of our consideration as well as our desired sample. And since we're doing the testing totally under like in a submerged situation in a saline solution, and so that's why it's the overall design like gives you the opportunity to test any kind of biological live tissue or soft tissue under saline solutions. The cleaning, I guess, comes in a preservative as well. When you get the sample, it comes in a preservative within a saline solution. We'll just take it off and put it back to the same condition during testing as well. Hope that answers your question.
Got you. So you don't, but I assume after you're done with the test, you probably got to spray this thing down with bleach and wipe the whole thing down and all that jazz. Or is that not something you really have to do with this apparatus?
Yeah, we will destroy the tissue because we will pull the tissue at its limit to determine what's the maximum strength on the tissue and at which point it tears. So that we're not going to reuse the tissue after the testing.
Okay, sounds good. Yeah, good work, team. A lot of good design work in there. And it'll be cool to see the machine at work here hopefully soon.
Thank you.
Any other questions?
Just to add, Dr. Tharbam, I guess I didn't answer Dr. Bachman properly. So if you mean that if like cleaning the whole equipment is a concern, then yes, it's very easy to like take off the arms. You just have to unscrew it, and the whole saline tub, it's made of polycarbonate, so you can always take it off, clean it, and put it back.
Oh, very cool. I saw Matthias said you can use like alcohol too, so it's not as
probably
not as aggressive as other stuff that you might need.
Right. It's just simple cleaning. It just has like saline water on it. You can always take it off and clean it with basic water and just saline solution and keep it dry and put it back.
Very cool. I used to do some research on implants, and we'd have surgeons come and actually do different implants. And I remember our stuff after a while, it just got all rusty and things would stop moving right. And it was a total hassle that I had never thought about at the time, but ended up being something I wish I had considered more when we had made some of our fixtures. But yeah, very cool.
Yeah, and also polycarbonate, it's compatible with like most of the regular alcohol cleaning liquids that are available in the market, like you use for basic cleaning in the laboratory. So it'll work. The cleaning is very, very easy on this equipment.
Very cool. Very cool.
Okay. Any other questions?
And one another question, I think it's for the image processing about the measuring the strain values. Is that routine that you guys developed, or it's just simply using the module that is built in for the camera, from the camera?
So basically what I did is I developed a LabVIEW program that can track the image. And then through there, we can export a graph that visually represents the displacement that's made by every single point of interest. We were supposed to further develop that in order to measure also velocity and strain and also angular distortion. But unfortunately, because of the COVID, I wasn't able to have the extensions needed for LabVIEW in order to develop that program. So I was only able to get as far as tracking the displacement in real time.
Oh, okay. So
Yeah.
what is the precision of that, your camera versus your image processing capability?
Sorry, what was that?
The precisions. Somehow you measuring the strain values, right?
Yes.
So how precise, what is it, like a 0.001 strain, or what's a 1000 strain? What's the like capability of that?
I did not get that far into it. I was gonna go ahead and edit the program for that as well after being able to test it with the actual program. But the resolution of the image should be able to track everything to a very precise measurement. But unfortunately, we weren't able to conduct everything all the way in order to fully develop the LabVIEW. So I'm not quite sure about the precision of the camera itself with real-time samples.
But the manufacturer, they mentioned that the precision of the camera, it's 1/10 of a millimeter. So this is the accuracy of the camera, and it's actually in the property when we purchase that camera from the manufacturer. Yeah, the data has been provided from the manufacturer, so, but we are not able to like see it in person.
Okay, thank you.
Okay, other questions?
I saw that you guys were supposed to use a gearbox. I was wondering if you could go to your assembly. Where would it be that the gearbox where number 2 is at?
Yes.
Oh, okay, so it'd be like a planetary gearbox?
Yeah, it's a planetary gearbox. It's made for exactly, we can get the gearbox according to the size of our motor shaft, and it's easy to mount. We just have to add it with our whole system to have the motor with its desired power.
Very nice.
Thank you.
Okay. Okay then, well, thank you, team. It was a very interesting presentation.
Thank you very much. Thank you all for being here with us.
Okay. We've got about 5 minutes before the next presentation. That will be Southern California Edison Open Conductor Fault team. So that'll start at 3:20. So stand by for 5 minutes while they queue up. If somebody on that team wants to grab. Okay. Thank you, everybody. I think we're ready to go. Can Steve confirm that he hears everybody?
Yeah, I'm in.
Okay. Okay, thank you. Welcome to Expo 2020, our first online Expo. This is the first day of the second week. We have a full plate of presentations each day from noon until 6 p.m. The next presentation in this session is the Southern California Edison Open Conductor Fault Team. Let me remind everybody that we have a Qualtrics survey where you can fill out or give some comments about the to provide back to the students and back to the department so that we can all improve. I encourage you to fill that out. You've got the link in your invitation. I will also post the link to that survey in the chat room. If there are no questions, then I think it's time for the team to start. So without further delay, this is the Open Conductor Detection on Distributed Lines team, sponsored by Southern California Edison. Go ahead, Blair, take it away.
Thank you, Mike. So good afternoon, everyone. My name is Blair Vidania, and like as Mike said, we are the Open Conductor Detection Group. Our sponsors for our project was Southern California Edison. Our SE liaisons are Ignacio Sanchez, Sean Wang, and Robert Lloyd. And our faculty advisor is Dr. Thorburn. So for today's presentation, I'll be introducing the team. I will also be covering the scope of work, background, and society impacts that our project has on the public. After myself, Stephen will talk about our project's technical requirements, our group scheduling. After him, Nancy would follow by presenting our final model and the process we took to get there. Kendrick will discuss our results and simulations. Matthew will present our detection logic scheme. And lastly, Jonathan will conclude our project findings. So as I said before, I'm Blair Vidania, and I'm the project lead for the spring semester of our project. Our group was broken down into two sub-teams. Our first team is a simulation team with Nancy Martis as team lead, and team members Kendrick Lin, Stephen Chang, and Jonathan Estrada. Our second team is our protection relay logic team with Matthew Guzman as a team lead. And along with being the team lead for the whole team, I was also part of the relay team. So for our scope of work, our main goal was for this project was to design a relay detection algorithm capable of detecting and de-energizing an open conductor before it hits the ground. But in order for us to do this, the simulation team first had to use the software PSCAD to design a distribution model to simulate an open conductor at different locations within the model. And once the simulations were completed and data was extracted from the simulations, the relay team had to analyze that data to be able to come up with threshold values for our relay settings. And along with coming up with our threshold values, our relay team was also in charge of designing the Boolean logic for the detection algorithm. And within the scope of work, it was also required for us to submit our final detection algorithm to our CE liaisons so they can test so they could test our trip equation and provide us feedback so we could refine and make our algorithm work better. So to give you all a better understanding of what our project is and where exactly it's taking place within the power system, I want to provide you all with some background. The first thing is defining what an open conductor is. An open conductor condition occurs whenever a power line disconnects from the power system, but it doesn't make any contact with any other surfaces. I know, like as seen in figure 1, for this figure, the conductor is actually touching the ground, but just to kind of show you that there's 2 remaining healthy phases, but 1 detaches. Our goal is to be able to try and, first of all, what's the word I'm looking for? I'm sorry here, to be able to detect it and then de-energize it before it hits the ground. And the second thing I want to explain to you all is kind of describing the main components within the power system. It could be summarized into 5 key components. Just be aware that there's other ones throughout the way, but for the most part, it's just important for me to identify these here. So starting at the start of the power system is the generation. This is where, for the most part, mechanical energy is converted into electrical. Once it's been generated, the voltage goes through a step-up transformer and is carried out by the transmission lines. From the transmission lines, the power goes to the substations, and then it gets stepped down. From the substations, the power is redirected through distribution lines, and from the distribution lines, it is delivered to the customers. The customers could be broken down into 2 main categories, which is either commercial or residential. For our project, our focus is being able to detect an open conductor within the residential customer section of the power system, as a yellow arrow is showing in figure 2. Now, being able to detect and de-energize an open conductor is a challenge that many utility companies around the world are still attempting to overcome. And the reason why it's so important is because distribution power lines can be located within populated areas that exposes them to an environment where they can easily be damaged. Open conductors conditions can occur due to vehicles crashing into power poles, objects such as tree branches hitting the conductors, or harsh weather conditions that may cause the power lines to detach, such as high winds or even lightning strike coming in contact with the actual power line. When conductors are damaged, they pose a serious threat to the public. They can cause hazardous electrical arcing that may come into physical contact with people or any surrounding buildings. And as many of you may know, here in California, some of these distribution lines could be located within dry landscapes, especially during the summer. So if an open conductor situation occurs and it comes in contact with that dry landscape, it could cause a serious fire and pose a serious threat to the public. So it's not only important, because it's a safety hazard for the public, but any damage that's caused by these wildfires, the utility companies have to be able to kind of, pay the price. So, and sometimes it's hundreds of millions of dollars in damages that could lead a company to kind of just go bankrupt. And with this said, I'm going to pass my presentation on to Stephen.
Thanks, Blair. My name is Stephen Chung. We'll talk about the project technical requirement and scheduling. Next slide, please. In order to complete this project, Southern California Edison provide a set of technical requirements based on their current power distribution system. Single open conductor happen on one of the three-phase distribution line at the residential load location. System voltage set at 24.9 kilovolt and current range between 50 to 17 kilo-ohm. Our design need to be respond within half a second, which means 30 cycle of waveform of sine wave. Next slide, please. Start on fall semester 2019. We mainly focus on research such as relay, phase shifting, power distribution theory. We attend as Southern California trainings. We practice PSCAD software, and also we develop the early stage of Boolean logic designs. Next slide, please. On phase 2, PSCAD team obtained the IEEE 34 bus distribution model. We stimulate an open conductor in 5 different locations with requirement as the relay team request. Then relay team fine-tune the logic algorithm, create a chip equation, and submit to Southern California Edison. Next slide, please. In this project, we learned the background knowledge about the power system operation and protection from Southern California Edison. We get familiar with software such as PSCAD, Accelerator QuickSet, and SEL Central Wave. Also, we learned the way to implement the logic algorithm into the SEL relay. For more detailed information, our teammate will talk on this project. Now, next we'll pass on to Nancy.
Thank you, Stephen. Good afternoon. My name is Nancy Martis. I am the PSCAD team lead, and I will be discussing the final simulation model we used for this project and the journey we took to arrive at the decision to use this model. Next slide. To get to our final model, we went through a bit of a process. We began with this initial design for our standard distribution model based on the technical requirements established by Southern California Edison, which, if you will recall, required for the open conductor condition to occur in a residential portion of the electric power system. Our model was designed to include zones of protection shown in the red boxes and they were meant to isolate the affected part of the system to ensure delivery of power to other parts of the system. After we had an initial design that we wanted to build, we got to work creating our model simulation using simulation software and collecting relevant data. Next slide, please. Power Systems Computer-Aided Design, also known as PSCAD, is a simulation software used to facilitate the study of electric power systems by enabling users to construct a circuit and run a simulation event. For this portion of the project, we needed to learn the ins and outs of the software in order to be able to construct our standard distribution model and extract data. Through our study, we learned that PSCAD comes with preloaded examples of various power system models, which can be used as a starting point to build projects with user-specific needs. We decided to try to use one of these models and modify it to conform to our project needs. This figure shows a two-bus system with feeder, and we decided to use it because we felt it closely resembled our initial idea for a standard distribution model. However, as we looked deeper into the construction of the model, we found, I guess, a major flaw. The model will only extract fault data conditions data for fault conditions such as line-to-line and line-to-ground faults. We learned that PSCAD doesn't actually have a component representation for an open conductor condition. We decided to go back to our original idea or our original plan of constructing our initial idea for a standard distribution model in PSCAD. Next slide, please. The figure shows the model that we were able to construct. Because PSCAD does not have a component for an open conductor, we decided to design an open conductor condition by placing a circuit breaker, represented by the green box, on the line that would open during the simulation event and provide us with open conductor data. Despite our best efforts, we came to the conclusion that our design was not complex enough to accurately represent a medium voltage distribution system. Our circuit was comprised entirely of ideal components and could not mimic a real working distribution system. Because we needed to collect meaningful data, our liaisons at Edison decided to provide us with a distribution model. Next slide. This is the IEEE 34 bus test feeder model, and it is a real system being modeled in PSCAD. The actual feeder is a three-phase radial distribution system located in Arizona. The 34 bus model is a 60 hertz, 24.9 kilovolt, 12 megavolt ampere system with various fixed loads and unbalanced loads connected to a main distribution substation. This system includes detailed information on line impedances, transformer connection and impedances, and load data. Due to limitations of the student version of PSCAD that we were using, we had to eliminate the regulators, which are highlighted in red in the figure. Since the regulators were responsible for updating the output voltage of the system's transformers, their elimination had little impact on the study. In order to gather meaningful data, we extracted open conductor data from 5 different locations throughout the system. For more information on this, I will pass it on to Kendrick.
All right, thank you, Nancy. Hi, my name is Kendrick Lin, and I'll be going over the simulation and results we acquired from PSCAD. Next slide. The following table shows the locations the team decided to conduct our simulation. The location is specified as a node-to-node connection within the 34 bus model. The figure on the bottom with red X's show the locations that we performed the simulations. Note, for the rest of my presentation, we will be focusing only on simulation number 3 for the sake of repetition, as the results of the other locations show similar characteristics. Next slide. After settling with the 34 bus model and getting confirmation from our liaisons as well as Dr. Nabed, we began focusing on our simulations. For us to perform the simulation, we had to come up with a solution to create an open conductor. But as Nancy stated, PSCAD does not have this feature implemented into the software. To remind you, Nancy mentioned the solution the PSCAD team came up with is to use a circuit breaker labeled as a green square shown in figure 1. This was our first step. Our justification for this solution is that an open conductor essentially is an open circuit where current flow is discontinued. The fundamental of a circuit breaker is a switch that opens and closes to disrupt or complete a circuit and allowing current flow. A circuit breaker will act as our open conductor that we can control and program the duration of the event per our technical requirement response window. After coming up with a solution and locating all the locations needed, we began implementing the open conductor and collecting data. Figure 2 is a typical location with load components connected in between each node. Figure 3 shows an example of how we connected the open conductor into each location. Next slide. Here are the results we gathered. The results we gathered consisted of phase voltage and phase current. Let me remind you again that these results only portray simulation number 3, bus 834 and through 858. Since this is a three-phase model, we need to extract data per phase to have a well-rounded and complete database. Each phase is color-coded per PSCAT's default setting, blue being phase A, green for phase B, and red for phase C. After analyzing these graphs, we can visually see that when an open conductor occurs, there is an obvious effect to the remainder two phases. The other two phases begin to fluctuate abnormally for a moment to compensate and balance the load among the two remainder phase. Not only is there a change in load being distributed to the two phases, there is also a phase shift, meaning the waveforms of each phase will shift horizontally or on the x-axis, which is the time domain labeled in seconds. After collecting this data, we can give numerical values to the relay team so they can come up with nominal values to program the protection relay. Next, Matthew will explain how the relay team was able to perform this part of the project.
Thank you, Kendrick. Hello, everyone. I'm Matthew Guzman, Protection Relay Logic Team Lead, and I'll be walking you all through the team's detection logic design process and final results. Next slide. So the relay team and I were tasked with designing the relay detection logic responsible for detecting an open conductor and de-energizing the line using the simulation results the PSCAT team had produced. To that end, there are a few key considerations the team and I had to keep in mind throughout the design process of the detection logic. Firstly, the response time of the detection logic could not exceed our detection time window. The greatest contributor to this restriction were the delay timers we used. Secondly, we had to keep the total number of input parameters as low as possible. This restriction was imposed mostly to ensure the detection logic was not so complex that it was unstable and unreliable. Lastly, we had to use parameters with the greatest chance or probability of successfully detecting an open conductor. These parameters would be selecting by analyzing the simulation data and identifying which behavior was most consistent throughout our simulations. Next slide, please. And here's what the team and I were able to produce. Our detection logic has a total of 5 parameters. In the early stages of our detection logic design, we had considered 7 total parameters, but once we started analyzing the simulation data and results provided by the PSCAT team, we were able to reduce the total number of parameters to these 5: 0, negative, and positive sequence voltage components, phase current, and phase voltage. Our design also includes delay timers for an added layer of reliability and relay logic grouping for added flexibility of the two groups of logic parameters. The parameters you see marked with an asterisk are not currently feasible by modern protection relays, but they are integral to our detection logic design, and we believe in the future these parameters will be implementable. Thus, we have decided to include them. So let's first jump into the detection parameters and how they were selected. Next slide, please. The graph here shows the 3 voltage sequence components of our distribution system model before and after an open conductor event occurs at roughly 1 second of simulation runtime. We analyze the simulation results half a second before and after the open conductor event because this represents our detection window of 36 system cycles, which is equal to half a second. This is represented by the orange and magenta vertical lines you see on the graph. Half a second before the open conductor event, the system's 0 and negative sequence voltage magnitudes are nearly 0, and the positive sequence voltage magnitude is about 0.83 per unit. This represents the nominal values we wanted to see for a healthy system for our model. At the 1 second mark, when the open conductor has occurred, we can see an almost immediate change in the magnitude of all three sequence components, where the 0 and negative sequence voltage magnitudes increase significantly and the positive sequence voltage magnitude decrease significantly as well. This behavior was observed consistently throughout our simulations, and thus we decided to use them as part of the detection parameters in positive sequence under voltage 27N, zero sequence over voltage 59N, and negative sequence over voltage 59Q. Next slide, please. Similarly to the approach we took with the sequence component parameters, we decided upon using both changes in phase voltage and phase current in our final detection logic design. Here we have both graphs for the system's phase voltage and phase current before and after the open conductor occurs at 1 second. Throughout our simulations, we observed that the amplitude of the phase voltage of the open phase consistently drop in addition to the phase current of the open phase dropping to 0. We also observed changes in the amplitude of the two healthy phases, currents, but the behavior of this change, whether the amplitude increased or decreased, was not consistent, and therefore we did not include a parameter in which the other two phases are considered for open conductor detection. Thus, we only included the phase voltage and phase current for the open phase via phase under voltage 27P and phase under current 37P. Next slide, please. As I briefly mentioned when going over the detection logic diagram, delay timers were used as added measures for reliability. There are two types of delay timers we used in our logic design. Pickup delay timers, represented by the top left number on the figure shown here, and dropout delay timers, represented by the bottom right number. The pickup delay's primary function is to wait the set amount of time before picking up any change in the logical signal entering its input. This acts as a kind of buffer and helps eliminate potential false positives that may have been triggered by temporary disturbances to the distribution system. For our application, we selected 15 cycles for the dropout delay because most of the open conductor signatures we observed during our simulation lasted longer than the 15 cycles. The dropout delay, on the other hand, will continue to transmit the logical signal that it received for the amount of time selected. This is used to ensure that the slower acting circuit breakers have the appropriate amount of time to fully switch open before the trip signal is dropped completely. Most modern circuit breakers switch open within 1 to 2 cycles, but some of the older circuit breakers still in use today have circuit breaking times of upward to 4 cycles, which is why we chose to set it to the dropout delay to 5 cycles. Our total delay time for the detection logic is 20 cycles, which falls within a 30-cycle detection window limit and leaves 10 cycles of breathing room for future adjustments and refinement. Next slide, please. And lastly, the final component to our detection logic design, relay logic groups. Relay logic groups are simply groups of parameters and their logical circuits grouped into one singular representative equation. For Schweitzer Engineering Laboratory relays, relay logic groups are represented by SV. Relay logic groups are used for mostly 3 reasons. They help organize special groups of parameters, they help clean up trip equations, and they help expand the usage of group parameters for other relay functions. For our detection logic, for example, the trip equation, denoted by TR, would be written as shown here by equation 1. If we group the sequence voltage parameters, the terms in the first set of brackets, and the phase voltage and current parameters in the second set of brackets as SV1 and SV2 respectively, then our trip equation is much shorter and simpler, as shown in equation 2. This allows these group parameters to be used for other functions in addition to circuit breaking tripping, without the need to re-enter the parameters individually for each additional function. Instead, we can simply enter SV1 into an alarm setting or assign it to a front panel LED instead of entering these 3 terms every single time. And now I would like you all to welcome Jonathan Estrada.
Thank you, Matthew. Hello, my name is Jonathan Estrada. I will now be concluding our project presentation. Next slide, please. Here is a summary of what we accomplished as a team. We have selected the IEEE 34 bus feeder circuit to accurately simulate a distribution system. By updating that PSCAD model to include breakers, we had then simulated open conductors and extracted data. That data was then analyzed to develop our detection logic. Next slide, please. We as a team completed many of the deliverables for the project. However, due to COVID-19, there is one item that needs to get done, validating the detection logic. To do this, we would then need to submit our detection logic to our liaisons at Edison to be tested. Based on their feedback, we would then make any adjustments to our tribute equation. If the logic was validated or approved, we would then program the tribute equation into the cell 351 relay to determine the probability of which the relay could detect an open conductor using our logic. Next slide, please. We'd like to take this time to thank our faculty advisor, Michael Dobron, as well as our project liaisons, Robert Lloyd, Ignacio Sanchez, and Sean Wang, as well as other engineers at Edison, such as Nagy Abed, Ed Wong, and James Timidara. For their guidance and support to the team, we thank you. Next slide, please. We will now be answering any questions you may have about the project.
Okay, thank you, team. We do have ample time for questions. Who would like to go first? You need to unmute your microphone.
So I guess I'll start off with a question. So it seems like you had kind of pretty good metrics for determining an open fault. What's the potential for using some of this on kind of SoCal Edison's grid to detect the faults at this point?
So when they first gave us or came with kind of introduced the project to us, they provided some guidance on kind of telling us what route to kind of stick to. We decided to pick these parameters because it already, these parameters would work with what Edison already has implemented in their power grid, as opposed to other companies like San Diego Gas and Electric. They're implementing a whole nother piece of hardware, which are called PMUs. And they're developing their algorithm by adding more to their grids. And I think that's one thing Edison just kind of made us aware of. Like, the issue is to try and solve it with what we have. And if it's not possible, then they'll look into something else.
Okay, but is there any, I wonder if there's maybe like they have some microgrid or some place where you could kind of just test it out and see how well it works for their purposes.
Oh yeah. So that was pretty much like the last leg of our project, was to actually submit it to them, and they have a laboratory in their Pomona offices where they're receiving like live information and stuff, where they have previous cases where they encountered open conductors or a high impedance fault, and they were going to take that data and our trip equation and run it through a simulation to see if it were to actually work, or if it worked, then how long it would take it to detect the open conductor. Yeah, but since like John stated, due to the COVID issue, they had to start working remotely, so they're not even allowed into their offices, so we weren't able to get that far.
Okay, thank you. Wow. Yep. Good work, team. It was really interesting presentation. I enjoyed it.
This is Mike Thorburn. Can you remind us how you distinguish between this open fault condition and some other load variation? Who wants to take that question?
So by load varying, you mean when loads obviously fluctuate throughout the day?
Yes. Yeah.
Okay.
You've got this signature for this fault, and there are signatures for all kinds of things. I was just wondering if you could remind us what's different about this signature, or how do you isolate it from other things?
So that's going to be part of, that's like the whole packaged answer, I guess you could, question you can say, where the simulation on PSCAD software would show a specific characteristic signature for an open conductor. So just based on running PSCAD simulations, we are able to come up with nominal values from the simulation that we can then set our relay to recognize those specific characteristics, rather than being a general algorithm where it's gonna get confused with multiple and different simulation different signatures. Sorry.
Okay. Okay. Thank you. Are there other questions? Okay, if not, well, let me thank you, team, for the interesting presentation. Our next presentation is going to be starting at 4 o'clock, so we've got 5 minutes or so before that one starts. That'll be the air quality control and sensor data team. For everybody in the audience, please remember that there's a Qualtrics survey. You can see the link to it in the chat room. I encourage you to fill out a Qualtrics response for each one of the presentations that you see today. Okay? So I think what we'll do now is we'll pause for a moment and pick back up at 4 o'clock in about 5 minutes. Thanks again to the California Edison team, and when the air quality control and sensor data team shows up, they can grab the screen. Thank you.
Good job, guys.
Thank you.
Thank you. Thank you.
Thank you.
Okay, it's approaching 4 o'clock. Do we have the Team 71 here?
Yes.
Yes.
Yeah, we're about to jump in.
Okay, so you guys can take a hold of the screen. While they do that, let me welcome everybody. This is Expo 2020, our first virtual Expo. Today and the rest of the week, we have a full complement of presentations in the electrical and mechanical engineering area. The presentations are being scheduled from 2 until 6 o'clock daily. Our next team is the air quality control and sensor data team, which is sponsored by a clean tech startup called SIA. And if there are no initial questions, I guess it's time for to make the presentation.
Is everyone here, Terrence, or are they still not in here?
Let's see, is Terrence here?
Yes.
Terrence and I are here.
And Andrew?
Yeah, I'm here.
And Leanne?
Yes, I'm here.
I think you're all here. Or maybe Yoon.
Yes, I'm here.
Okay. So,
All right. Well, then I guess we'll get started. Good afternoon. We are the SciLife Smart Water Management team, and we're doing the air quality sensor and data analysis. Team members, I'm the lead, Andrew Seelman.
I'm Leanne Cerritos.
I'm Terrence Sarmiento.
I'm Yoon Beck.
And our advisor was Professor Ayers Lin, and our liaison, SciLife. Can we? Okay. So just covering the agenda of the presentation, Yoon will take us through the project background. Leanne will do the organization of the project, and then me and Terrence will go through the technical end, such as the project components, sensors, and then Yoon will take it away with the summary.
So our project was given to us by our sponsor, SciLife. Their company is based around a smart water management system that allows their customers to monitor their water usage. This is done through the Sci mobile app, which also alerts the user of any water activity that might be going on without their knowledge. And they also have controls in place that shut off the water source to prevent any leakage from property damage. One of Sci's main goals is to provide homeowners, property managers, and tenants peace of mind through their technology. In addition to their water system, Sci plans on expanding their versatility to monitor different aspects of the home, such as security, energy, and air. This is where our team comes in. Our objective was to design and develop a wireless, low-powered air quality monitoring system that detects various compounds in the air and have the status of the air easily accessible to the user. In order to achieve this, there were several things we had to do. First, we had to determine the components to be used. We needed to choose which harmful compounds we wanted to detect in the air. Then we needed to implement low-powered wireless communication that would send the data to a gateway to be stored in a database we created. And finally, we were to create an enclosure that would house this whole system. Our end goal was to give the user more knowledge and power to maintain good overall air quality in any given environment, and to have a system efficient enough to be used in hospitals or any clean rooms, and help anyone that wants to achieve LEED certification for their facilities.
So I'm going to talk about the project organization. For this project, we partnered with SciLife and worked with their liaison, Anthony, along with our group leader, Andrew Seelman, who worked on the embedded system, as well as helped us each with our ADC, I2C, and Laura. Our advisor for this was Ayers Lin, who advised us for this project. He assisted us with the both embedded system as well as any programming questions that we might have. Our group consisted of Yoon Beck, who worked on the embedded system, part of the communications, as well as the dust and methane sensor. Myself, who also worked on the embedded system, the TVOC and temperature sensor, as well as I2C, and Terrence, who worked on the database and communications, which was the MySQL and Laura. One of the project requirements was to design and create a device that is compatible with the system that SIA already had implemented in their water system. Therefore, we used the same microcontroller and LoRa module that they have for their system. We also wanted to include an LCD so that the customer could see the readings themselves, as well as a long battery life so that the user would not have to change the battery as often. When researching for LEED requirements, the most common compounds to be detected were TVOC, CO2, methane, and dust. So those are the ones that we chose for our system. The database that we used was MySQL, and then we wanted to include a clock, so the RTC, so that the user may see the readings in real time. Also, we used -20 to 50 degrees Celsius for our range so that it could be used in different regions around the world. As stated previously, we use the same microcontroller, which is a very good one. It is low powered, affordable, efficient, and compatible with our system, meaning that the pins were compatible with the both the sensors as well as the LoRa module that we used for our system. So when doing research, we went through a bunch of sensors that were that could detect the compounds that we wanted for our system. Specifically for this trade-off table, we compared different temperature and humidity sensors, and we narrowed it down to 2. The one we chose for this system was the one to the left, which is the BME 280. The interface for this system was I2C and SPI, which was ideal because another one of our sensors also uses this interface. The temperature range met our requirements, which is -40 to 85 degrees. Also, it had a bigger range when it came to humidity, 0 to 100, compared to 20 to 90.
A bonus when it came to the sensor is it also detected pressure. Although price was a little bit higher with these specifications, we decided on this sensor for the temperature and humidity. Also, when comparing dust sensors, we narrowed it down to 2 as well. And we decided to the one on the left, which was the sharp sensor. Although it was analog, it did detect smaller particles. So that was better than the one to the right. As well, it had a bigger range when it came to the voltage. And again, the price is a little bit more expensive, but it did have better ranges. In the end, we decided on these 4 sensors for our system. So BME 280 for the temperature, PME 2.5 for the dust, CCS 811 for the TVOC, and then MQ4 for the methane. Now I will hand it off to Terrence, and he is going to compare the communication modules.
Thanks, Leanne. On your screen is a table that shows the comparison between other communication modules that we could have possibly used instead of LoRa. Even though it was specifically designated by our liaison for us to use, we still did some research of our own to find the reason why they chose it, aside from the fact that it is what they currently use for their established water management system. We are all probably familiar or have an idea about Wi-Fi and Bluetooth, so the only question is, what is LoRa? LoRa stands for Long Range Radio, and it is a module that is specifically designed for long range and low power communication, which in return enable its power supply to last longer. Now that we have an idea of what LoRa is, let's go over the possible reasons why our liaison chose it. As we can see on the table, when it comes to operating range, LoRa has a very huge advantage over Wi-Fi and Bluetooth, having a range of up to 3,000 meters, which for reference is more than the entire length of the Hollywood Walk of Fame. It is suitable for the purpose of our project because SIA wants to implement the air quality system onto commercial buildings, which tend to have a large area that Bluetooth and Wi-Fi can't support. So based on these numbers, LoRa wins this aspect. In terms of capacity, the LoRa module can connect to 1,000 nodes or 1,000 of the units of the air quality system. It is considerably a high number of connections, which is more than enough for a building. As I previously discussed, the LoRa module has a low power consumption and it is about 4 microamps. Wi-Fi and Bluetooth consume 0.9 milliamps and 30 milliamps respectively. This power rating of the LoRa helps towards the overall power consumption of the components and would allow for longer maintenance of the system when it comes to the battery. Next on the list is the data transfer rate. Wi-Fi has the highest transfer rate with 7 Mbps using the Wi-Fi module that you can see on your screen. Although it is colored in green, it is not preferable for our project because according to our liaison, we only need to send small amounts of data at a time. So even if the data transfer rate of LoRa is the lowest, it is still more suitable for our project because there's no need for sending huge amounts of data. In terms of the price, we tried finding the prices of each module and we found that a Wi-Fi module can be bought for $3. LoRa module comes next with $6, while a Bluetooth module costs $7. Even though the Wi-Fi module is half the price of our LoRa, the previous categories already offset its price value. And so based on this table, we can definitely see that the most suitable communication module for us to use in this project is the LoRa. Now, I am going to talk about the overall design of our project. The air quality system consists of a microcontroller, which is the TI dev board Leanne mentioned a while ago. Attached to the microcontroller are all the sensors that will gather the air quality data we need. Then here comes the LoRa module, which completes the whole system. The purpose of the module is to wirelessly send the data to another LoRa module acting as a gateway that is connected to a computer via UART port. The idea is to have multiple units installed in different locations, such as offices, restrooms, hallways, and etc. And still communicate to the same gateway. All the data received will be gathered and stored in a database using MySQL, which I am also going to cover later in this presentation. Now I am going to move on. Now I am going to turn over the controls to Andrew.
Thanks, Terrence. I'm going to cover the control block diagram on here. On the left, you'll see our basic schematic, and on the right, more of an animated picture of our system. In the middle is our TI MSP430 microcontroller. Our analog sensors are the methane and dust on the top and bottom, and our I2C sensors are on the left and right, being the temp sensor and the TVOC sensor. And then we have the LoRa to the left. The analog sensors are, their analog output is sent to our analog inputs of the TI microcontroller. And then our two I2C sensors are connected to the SCL and SDA lines. And then our LoRa is hooked TX and RX to the microcontrollers RX and TX respectively. Now I'll take you through a couple of our interface protocols. The first one is the I2C, which stands for Inter-Integrated Circuit. It's a serial communication that allows multiple masters and slaves. In our project, we only have one master, which is our microcontroller, and then two I2C sensors are our slaves. I2C is a two-wire communication, having the SDA, which is the data line, and SCL, which is the clock line. So when our microcontroller is ready to communicate with our sensors, the data line is driven low, and then the clock starts pulsing. And on every rising edge of the clock, the data is read, and if it's a high, 3.3 volts, it's a 1-bit, and 0 volts is 0-bit. It'll do 7 of those for the address of which sensor we're talking about, and then the 8th bit being the read or write bit, whether we're trying to read data or write data. And then the sensor will send back an ACK signal, which is an acknowledgement that it received the address. Then it pauses for a second, and then the SDA drives low again, and then the 8 data bits are sent back to the microcontroller, and then the microcontroller sends the ACK bit, acknowledging that it received all the whole byte of data. For UART, which we have between the microcontroller and the LoRa, that stands for Universal Asynchronous Receiver Transmitter. It's also a serial communication with 2 wires, but in this case, the 2 wires are the TX and the RX lines, where TX is the transmit, and that transmit goes to the opposite components RX and vice versa. And it's asynchronous because there's no clock that's driving it. It just starts by the TX line being driven low, which is the start bit. Then a high pulse would be a 1, low pulse is 0, similar to the I2C, and it will send 8 of those bits until it receives a stop bit. And to tell you that the UART transmission is complete. Finally, we have the ADC interface, which is our analog to digital conversion, which we use for both of our analog sensors. So when our sensors are reading data, based on how high or low that data is, it outputs a continuous analog signal. And our microcontroller receives that analog signal and matches that signal to the closest digital signal that it has. And our microcontroller is a 10-bit, so it has 2 to the 10th digital levels where it matches the closest analog to the digital level. And once it's all in digital, then the microcontroller can understand the data and store it into the variables. Now I'll take you through the flowchart of our software, of our system, and basically how it works. So we start by sending the address of our TVOC sensor through the I2C pins The TVOC sensor acknowledges and then will send back the data that it's stored in its registers. We repeat that process for the humidity sensor, where we send the address there, and then the humidity sensor will send data back. After those two sensors are complete, we do the ADC conversion on our methane sensor. When it's complete, we receive that data, store it into our variable, and then similar concept for our dust sensor. Once all that data is stored in our variables, then we display all the values on our LCD screen, and it'll repeat every few seconds as it updates. RTOS is kind of the structure we used for our software, whereas most programs are more linear. RTOS is it's kind of a structure that switches between tasks rapidly. It avoids the buffer delays in that, because usually you'd have to fill a buffer with all the data, spit it out, fill it, spill it out, which takes time every time you do that. So it avoids that by just doing every task simultaneously. And really the main reason we implemented it is we can get all our tasks done in a preset amount of time. So now I'll give it over to Terrence, and he'll talk about the database. Terrence? Are you there?
Well, Terrence is flipping the screen, right?
Yeah. I don't know where you went.
Oops. Looks like he dropped off.
Let's see.
Oh, somebody's back.
Sorry, I got kicked out of Zoom.
Okay. Well, I just
apologize.
finished the RTOS page, so whenever you're ready with the database.
All right. Sorry about that. Like I previously mentioned from our conceptual design a few slides ago, we plan to use MySQL to have the air quality data stored in a database. Sorry. MySQL is an example of a database management system, or DBMS in short, that allows to store, access, and manipulate data. It can be compared to an old card catalog that stores catalog cards containing information about each book, such as the author, title, publisher, and so on, which libraries used before online catalogs took over. Inside the database management system are databases, which are structured, organized, and systematic collections of data, while a data is any piece of information about any object or anything which could be as simple as a name, color, and weight. Here is an example illustration of a database management system. DBMS serves as the connection between databases and users trying to access specific data, such as staff details, customer accounts, and stock levels. And now, to conclude our presentation, I'll pass it on to James.
So as for our results, we were able to obtain data from the sensors and have the built-in LCD cycle through different sensor levels, which was set to a number scale. And by setting its parameters, we had the lower modules communicate with each other and relay sample code structured similarly to how the sensor data would have been transmitted and received. We were also establishing a database in MySQL to properly store future data and designed at PCB. However, due to the COVID-19 virus, we were not able to implement the wireless communication to our system, which means we never got to store real-time data and manipulate them for future purposes. We weren't able to print out our PCB design or build an efficient, eye-pleasing enclosure for our whole system. In the end, we gained a lot of experience dealing with different interfaces such as I2C, analog, and UART. We learned a lot about wireless communication protocols and creating and organizing databases, and fortunately dealt with project ending circumstances. Thank you very much for listening. And if you have any questions, please ask.
Okay, thank you, team. That was a very interesting presentation.
Coburn, I think we should give a round of applause to Andrew, Yoon, Terrence, and Leanne for a very nice presentation and project. Thank you very much for all your hard work under difficult circumstances.
Thank you.
Thank you.
We appreciate it.
Okay. Thank you, Ray. Let me ask a question. How long do you suppose it would take to complete the work on this project and actually have a fully integrated and tested unit?
I would say that we would have to become kind of proficient with some sort of CAD program probably to do the casing, which I don't know, that maybe a couple weeks to a month, maybe to get a one that we really like. As far as the PCB design, I mean, we have all the components we need, so it maybe wouldn't take too long, maybe a week for that. So I think if we had another couple months, I think it could easily be completed. The problem was we got held up on the wireless communication, which we kind of focused a lot on and it was kind of confusing, so we didn't make it that far on that part.
Okay, thank you. And then I had another question. Do you have any, say for lack of a better phrase, like available slots? If I wanted to add another sensor, like say a carbon monoxide sensor or something, is that something that can be added to your system, or would that require a redesign?
No, that would be easy to implement. Yeah, because we set it up to, I mean, our microcontroller had at least 2 or 3 more input output pins that we could probably use for that. And yeah, it wouldn't be, I mean, I guess it depends on the interface of those sensors, because if it's something like analog or something, it'd be really easy to implement because we already did it. If it's something kind of new, we might have to change the software a little bit, but I would think if it's like an analog output, it would be really simple. Maybe even I2C, because we already have those lines hooked up as well.
Okay, thank you.
So you're running RTOS as an operating system on the TI chip?
Yeah, we're using it's what was it called, Code Composer Studio, and we had our professor, because I took embedded with him, and and we learned RTOS. So it's kind of just in the software where you set up the RTOS as Q. They kind of, it reminds me of interrupts, so where you do a task and then you interrupt out and do a different task and interrupt, that's kind of how it seems to me.
So you didn't really write anything in C on the TI chip?
We did write it. It's still C. It's it's done with like pointers and interrupts. It's kind of a confusing way to do it, but it does. I mean, it's probably the best when you get it working. Obviously, doing it like more linear is probably easier, but it's more barbaric. You just kind of do something, then do something else, and do something else. Where this is, you do something and then you could switch, and if that one task gets held up, it doesn't hold up the other tasks. So it's probably a better way to go at it. It is a little confusing to follow the flow of it, I guess.
And as long as your customer knew what you were doing and were happy, then that's cool.
Oh yeah. As long as it worked all good, I'm sure they wouldn't dig too deep into it.
Okay, I'm going to shut up for a little bit, and you can come back to me a little later.
Okay. Are there other questions?
This is Carl Salinas, Industry Advisor. I guess I don't know if I missed it or not, but when you started talking about the database and the RTOS, could you say a little bit more about the sampling rate and the amount of data that you would be generating, say on a sort of typical daily schedule? Or I guess I'm trying to get an idea of how long battery life is relative to what data you're capturing, and kind of what's the time span there?
Well, we were trying to cycle through all of our sensors probably. For testing, we did it fast, but when we really implemented it, we would slow it down to probably once maybe or twice a day, I would say, just because we want that battery to last a long time. So we really want our sensors to be in sleep mode a lot of the time. So they're not drawing much current. But yeah, obviously for testing, we did it quicker just to test. But I didn't think, air quality in a room would change so drastically that you would need to measure it more than maybe a couple times a day. That's what I was thinking for sample rate, because I don't want to be sampling too much where it's constantly drawing current and then our batteries are dead very quickly.
Yeah, I guess I would say that that you might want to really look at that requirement. I mean, I understand that for testing purposes, you need to generate data within a short amount of time. But I think also for practical purposes in the field, that sampling rate might not be often enough for some things.
Yeah, we were playing around with different ones. We didn't know exactly what would be the right sampling rate for this kind of application, where we don't think things are, the air quality is very volatile, so it might not change much. So we were kind of trying to play around with what would be, where we could catch the changes, but it's not too much where we're drawing too much current. So we were kind of, in the middle.
Yeah. I guess what comes to my mind is you sampling for something like methane. The concentration of methane changes a little bit, and you could be in a lot of trouble.
Yeah, that is true. Yeah, I guess it depends your main application for this.
Yeah.
If it was something detecting a gas leak, yeah, you might want to be more frequent with it. Yeah. You're right.
And just so I'm trying to put my head around this project. It's the first time I kind of get into it. So who is the user? Is it sort of like a security or watchman kind of person that's walking the perimeter of the property and is sort of checking up on different areas, or is it someone in a control station that's kind of actively monitoring the state of health of a facility?
Do you guys want to take that?
Yeah. The idea of SIA is to implement this first onto commercial buildings. So I assume the system would be monitored by the maintenance, those who also work on the maintenance of the whole building.
Yeah.
But if this is going to be applied to households, then it will be the owner of the house themselves. So
yeah, I just this comment. I mean, I could see a lot of areas where this technology could be used. Of course, as you're describing in buildings or complexes like that, as well as homes, but also in agriculture. A lot of things happen when they're filling silos with grain. There's a lot of dust. A lot of things happen when animals are cooped up in barns, and chickens and cows that are producing methane and other gases. So it could be a broad spectrum of applications for it.
Yes, that's true.
All right, thank you.
I have another couple of questions with regards to the power system. First off, was it actually a requirement that it be battery powered, or could you have this thing hooked up to DC or to AC power? And secondly, do you know which of your components was actually consuming the most power?
It was not a requirement that we had to do battery, but I didn't know exactly, because we kind of wanted it as its own little package, like comes with everything. You just kind of put it on the wall. I guess for more, like if it was in a hospital or something else, it could probably just be plugged into the, probably plugged in. But if it was more like a consumer product, I would see it more, I don't know, like hanging up in the corner of a room where, I don't know, you don't really want a long wire all the way to an outlet or something. So that's that. As far as what drawing the most current, pretty much anything that's active, that's not sleeping, is drawing a pretty good amount of current. So we really want everything in sleep mode as much as possible, because anytime and the LoRa, anytime we have to transmit, huge spikes in drawing current. So
Yeah, that's actually what I was getting at. I think that it would be your communication system that's probably consuming
Yeah.
the most power.
Yeah, there's huge spikes on a transmission. Yeah, really big spikes. But yeah, but honestly, even the sensors themselves, if they're constantly reading, they're drawing a lot of current. So we really want them asleep for a lot of times, and then that's why we're taking maybe one reading a couple hours or something, just so we're not really drawing that much current. I guess if we're plugged into the wall, that's less of a concern. It depends how often you really want to see this data, what application you're looking for.
Okay.
Yeah, that's why also important for the selection of LoRa and the MSP 430 because of their low powered operation mode.
Yeah, their sleep current's really low, obviously, but yeah, we don't want to transmit too often.
Okay. Ray, did you have some follow-up questions you wanted to ask?
I was going to shut up and let other people ask questions first, if there are others.
Are there other questions? We still have a few minutes.
No,
Hi,
I'm good.
my name is Ahmad Al Ubaid. I am also part of, I work over there like inside life, and I know you guys had like a lot of problem with the LoRa module, but you guys did a hell of a job. You guys did a good job, really good job, and I'm really amazed. Thank you so much, guys, all of you.
Thank you. I appreciate it.
I have a question. This is Charles Liu. So Andrew, this is a follow-up question regarding the sampling. There are some commercial products which have the sensory system embedded within their air purifier, for example. So sometimes they want to test how efficient their purification system works, and then also that probably needs some more frequent sampling. How easy, I'm asking the whole team, not necessarily Andrew himself, how easy if we could leverage the technology to those kind of commercial products, saying that we have an embedded part that's built in a air purifier, for example.
So you're saying it measures the air quality and then actually purifies it too? Is that what you're saying?
Right. So you constantly want to monitor the how efficient the purification is, the process is doing. Right.
Yeah. I mean, we're getting all those values that we stated earlier. You know, like CO2, methane, dust, all that. So, you could see what you're trying to purify, what you're trying to remove from the air, and you could see, I guess, how good of a job you're doing based on the readings, maybe the before after of the purification process, if how much was removed, if that's kind of what you were getting at. And is that what you were asking? Like if there's a purification in the room and you're trying to test how good of a job it's doing, is that kind of what you're saying?
Right. How can we use the technology you guys have developed to facilitate the monitoring of the removal of different particles or different compounds from the air, right? So that might need a more frequent sampling than what you plan, twice a day or that range of frequency.
Yeah. I mean, that's a again, yeah, it might be application to application with, like I said, how often we want to sample. Something like that, yeah, maybe we need to do it a couple times a minute even, or something like that. But yeah, it just would draw more power, maybe even, and if they don't mind plugging into the wall, I guess it's really not that big a deal. You can sample all day, who cares? But yeah, if we're trying to keep it one little sleek package, which was kind of our idea, then yeah, the battery life was a big deal for us.
Thank you.
Okay, thank you. I think we have time for one more question. Ray, do you want to go ahead and ask? I know you've been waiting.
Well, I have two quickies, and maybe this is for Ahmed of SIA as much as for the team, how much of a stretch would this be for a sensor to detect mold, bacteria, or viruses?
Yeah, I actually thought about that, but then I guess we'd have to do research on, what compounds create mold or, create those viruses. Like, hey, maybe at this perfect level of CO2 and oxygen and this and that, that's where mold really loves to grow. So maybe we set our sensor for, hey, if you see those perfect conditions, watch out, or change it, I guess, right?
Oh, good.
So, yeah, I would think you could do that. It'd be as easy as looking up or, doing research on what conditions cause mold. I'm sure temperature plays a huge play also. Humidity, we have all those. We all have all that info. So, I mean, we could just tweak our, our code to say, hey, if it gets to this level, change or do something, make it dehumidify, whatever.
Good, good. And just one quick question for Terrence.
Yes.
Talking about MySQL, what's a card catalog?
A card catalog is an old-fashioned thing that you guys are laughing. I know you know about that. So
I'm not old enough.
I've learned that when I was in elementary. I mean, we were forced to learn that because that's what libraries had been using before technology took over. I've read articles that said schools are throwing out their card catalogs because they're relying now on online library tools. So yeah.
Okay.
I was just teasing you.
I know you are.
Hey,
All
thank
right.
you, everybody. Great presentation.
Yes, it was a great presentation. Thank you guys very much.
Thank you, guys.
Good job. Interesting topic.
It is time now to move on to the next presentation. This is one of our UPS auto package sorting presentations. This is for bag handling control. Is the team already present?
Yes, sir.
Abdullah, Jose, Mon, etc.
Yes.
Yes, we're present. Yeah.
Okay, so you can go ahead and grab the screen. Go to share screen and just take control. While they're doing that, everybody please remember that we've got this Qualtrics survey. Please, you can see the address for it in the chat room. If you need another copy, let me know, I'll send it to you. We do want your feedback with regards to all these presentations. The students will benefit from it, as will I. Okay. Is the UPS team ready?
Yeah.
Then go ahead, take control.
Yeah. So we are the UPS Automated Small Package Sort System Control team. This the presentation. Yeah, I'm gonna go over, my name is Mon, and I'm gonna go over the introduction in the background. Right now at the UPS facility, when the bags are full, there is a person who comes over and sees that the bags are full. He lifts them up, he zips them up, he puts on a label, and then he throws them in the conveyor belt that goes towards the UPS trucks for delivery. And we are trying to make that process automated, as it will save as it will save time. And the objective of this project is to design a fully automated small package bag handling system. Our goals are to design a supervisory control with data acquisition systems, design and construct the controllers for motor functions and restocker communication, create solutions for intrusion detection and bag detecting. This is the organization chart. These are our like system requirements. And now I'm going to pass it over to Jose, who's going to go over the system overview. Jose?
Howdy. Okay, so we can go to the next slide. So I'd like to begin by introducing the main components in our system. On the far right, we have our master controller. This houses our PLC as well as various other subcontrollers. For example, one that controls the wireless communications to our restocker cart. This cart is what will go and fetch more of those forever bags when the system is out. And then on the left, we have our gantry robot. This can move around that entire XY plane that you see, as well as rotate. And this also has subcontrollers for all the gripping and zipping functionality related to the bags. If we move on to the next slide, this is our controls hardware architecture. So as you can see, the heart of this is our PLC. It receives input from an operator panel, and then it will send a software enable as well as data to all of our Arduino Mega based subcontrollers. And so we have 3 for movement. These are motor controllers, as well as 1 for system sensing. And then we also have restocker communications modules. If you go to the next one. So from a topmost level, we organized all of our functionality in terms of operational modes. So here you can see we have a mode for things like startup and reset, as well as gantry mode and operation. So if I run through this really quickly, we always start from that startup reset mode, and this happens anytime we have a fault or we cycle power. And then from there, depending on whether we, or depending on the operator input, we will either go into a debug mode or into the part of the system, which is gantry operations. And from there, we'll be actively monitoring the bag to see when it is full, so that at which point we can zip it up and apply a label and transfer it over onto the conveyor belt. Now, if at any point we run out of bags, then we issue that restock bag command. And then, the gantry robot will move over to the side to allow the restocker to resupply that slant table with more bags.
Unmute and start video.
Okay, we can move on to the next one.
Okay.
So this is just a sample flow chart. So for within each of these modes, there exists a set of corresponding operations and instructions. So this is for startup and reset. As you can see, we always start by making sure that our e-stop is not pressed. We run through a safety check, and then we go through and reset the gantry, the encoders, and make sure that we have communications with all of our components. And that's an overview of our system. If you go to the next one. So now I'm going to pass it on to Dom, who's going to go over intrusion sensors.
Hello, everyone. This semester, I've been working with the Programmable Logic Controller, PLC for short. For those of you who do not know what a PLC is, a PLC is an industrial computer that evaluates the state of an input, and based on the program, it'll determine the state of an output device. This semester, we've been able to run DC motors, emergency lights, and indicators. But one of the biggest accomplishments we have had this semester is programming the intrusion detection system. This program will help detect intrusion if anyone ever tries to enter the gantry. And it'll also detect if any bags or any boxes do not fall in the bag. Next slide, please. This is how it would look if we were to mount the photoelectric sensors that we're using onto the gantry. Each blue circle is a sensor, a photoelectric sensor. And you can see that each one has a label. This label will help indicate where each wire for the input will be wired to the input of the PLC. And also this, the main purpose for this schematic is also to help others and for future teams to help locate where the sensors are, just in case if any of the sensors is a malfunction or maybe it gets kicked and it doesn't align with the other sensor. If you guys see, you can go back, please. The red dotted lines are the beams. You can see a square is formed with the group of sensors. That'll help detect if anyone tries to walk inside the gantry, and the group of sensors that form an X, that'll help detect if any boxes do not fall within the bag. Next slide, please. These are the photoelectric sensors that we're using. So each sensor will have a beam, a through beam, and in order for the sensors to work, they have to work in pairs. So the indicator light on top of each sensor will turn on when two of these sensor beams are aligned directly at each other. And the way to code them in order for them to work properly and to detect intrusion or an object is the arrows on the back of the sensors. They have to be facing an opposite direction. This will indicate that you have a sending and a receiver. Next slide, please. This is my test bed. To the left, you can see an indicator light, and that's what will turn off if any of the beams from a pair of sensors are broken. The biggest part or the hardest part about wiring these sensors was there wasn't enough space on the voltage and ground terminals on the PLC to hook up all the 12 wires, power and ground cables from the sensors. So what we had to do was jump the voltage and grounds from the PLC terminals off to terminal strips just so we can power every single sensor up. Next slide, please. This is what the code looks like using the RS Logix 5000 software. We used a total of 12 inputs because those are the sensors, and they're labeled as local 1, data 8, local 1, data 10, etc. And the only output that we used, which was indicator light, was at the bottom right. It's labeled as local 2.0, data 15. Next slide, please. This is the schematic I have created on AutoCAD Electrical. It is how to wire each sensor. Off to the left, you can see these are the sensors, and each one will have a wire going to the input side of the PLC, and each sensor will have a voltage and ground. If you look to the right, the bottom right, we'll have a green light that was the indicator light. It's going to go to an output on the PLC and to ground, and that is how you wire the sensors. Next slide. Thank you. I'll be passing it off to Jose again.
Hi. So one of the more interesting challenges with this project was getting a like a commercial product to talk to our development units, essentially, because the PLC, like I said, is a commercial product, and then our controllers are all Arduino based. And so for that, we chose we needed a wiring standard and a communications protocol. So for wiring, we chose the RS-232 wiring standard, which is kind of redundant. And then also we evaluated several communications protocols. Our requirements were they needed to be robust enough to send commands and receive feedback. They had to be implementable on an Arduino, compatible with our point IO adapter, and they had to be low cost. And so two main options were explored: the Modbus RTU protocol, as well as an ASCII implementation, or implementation of the ASCII standard over RS-232. So if we go to the next slide, the Modbus RTU. So Modbus, it's an open serial protocol that's used widely within the industrial automation or within automation industry. And RTU is a remote telemetry unit, and that's a microcontroller that interfaces with sensors or real world components. And part of the reason why I chose this is because it has successfully been implemented by automation enthusiasts, so PLC and to Arduino communications. And it follows the master-slave architecture, where master initiates a request, and then a slave performs a response, and then sends back a message, and then the master receives it. So we go to the next one. So this image is primarily, or what we were trying to implement, and that is what's called a frame format for a message. And so what's cool about the Modbus structure is that it has a component for what's called a function code. And this essentially is built in and it says, hey, like, this is the operation that I'd like to run. So whether that be a read or a write, and depending on whether we're writing to individual bits, so bit-specific addressing, or to an entire register. Then we have our data, and then what's called a CRC check, and that's essentially just an error check, and then at the end. So can we go to the next one? So there were two main options, which were to develop our own library of functions or to source one out. And for this implementation, because it had already been successfully, completed, I went about sourcing in library, and that involved becoming really familiar with the specification and then testing a whole bunch of different candidates, if you will. And so this was my test bed, and my procedure was as follows. So to test read and write functionality, or to test read functionality, I had this potentiometer, and that was for an analog input, so we could read the resistance level. We have a button, and that's for a digital input. And then using an application that simulates a Modbus master, I was able to write to all of any of the pre-configured registers that I made on that Arduino Mega. And if a value went above a certain number, then it would blink that LED. And so that was successful, and this implementation was like ready to go. But if we go to the next one. Unfortunately, due to prohibitive costs, the Modbus implementation had to be abandoned. So the Modbus specific modules for our PLC were beyond our budget. And so instead we pivoted to this ASCII standard implementation protocol. And for this, we had to develop our own library of functions based around some modules that the team already owned. And this is the new frame format. This is taken from their documentation. And so it's similar. And I actually created a messaging standard based on this. It's sort of like a mix between that and Modbus, which I'll detail later. But in the next slide, this is a flow chart for the read operation. And so as before, we always configure our Arduino device based on the serial or protocol. So things like the baud rate, like how many bits to a word, or I mean to a byte or a character. Then we instantiate our data registers, and then we poll for a query. And then upon receiving a query, then we move to this update subprocess. And then whether the master is requesting some information or wants to write, we will either parse the message and then update our registers, or we will complete a handshake and then create a data packet and then send that out. And so if we go on to the next slide. So like I said, taking some inspiration from that Modbus protocol for their message structure, I set some new standards. So I always have a fixed length. Because this frame format doesn't have a built-in error check, one way to just make sure that, we're not losing information or we have a good message is to have a fixed length. And then within that length, or within that message, I broke it up into two components. The first one being a function code, and then the actual message. And so the function code is 4 ASCII characters, and that can detail a whole bunch of different instructions. And then lastly, we have our message. So one such example is, for example, if I want to instruct one of our motors to move forward, then I could send the ASCII character F, as well as the data, or the number 5. And so then that would say, move motor controller forward to position 5. Can we move to, and this is the struct in Arduino. And so this essentially is just like all the various boxes that hold this entire message. So it's held within one-dimensional arrays. And because we chose 8 bytes to a character, or 8 bits, that's like 1 byte. And that's per message. And this essentially takes what we see below at this table and puts it all into code, if you will. And now I'm going to pass it on to Pedro, who's going to talk about motor control.
Yes. So this is the main test bed, I'm sorry, there's a test bed using the rotary motor that's supposed to be attached to the gantry robot. This is created to make sure that the actual gantry isn't damaged. through the testing phase of the project. Go to the next slide, please. So on this slide, the schematic of the Arduino is wired with all the components is shown. The computer sends a signal to the Arduino to tell everything else to do its job. Pin 5 and 6 are the pins that are going to tell the motor to move forward and in reverse. Pin 4 are the limit switches, and those prevent the motor from overshooting the wanted destination. If the motor hits one of the limit switches, the motor will stop. Pin 2 and 3 are connected to the encoder. This shows a number on the serial monitor representing the position of the motor on the gantry. Pin 2 is assigned to the motor going in reverse, and pin 3 is assigned to the motor going forward. Go to the next slide, please. This next slide is to show just some code of the encoder, how it's going to work. And if pin 3 is low, then the number will rise, meaning the motor is moving forward. And if pin 2 is low, the motor goes down. I mean, the number goes down, meaning the motor is moving in reverse. Next slide, please. And we don't want the motor to stop instantly and cause any trouble, so we want it to come to a soft stop. And this would be the code that makes the motor stop softly, and it won't just instantly stop and damage it. Next slide, please. And I'll pass it on to Mon with the controller build.
Hi, I was in charge of building a controller. This is a prototype of the controller, which consists of Arduino Mega, an RS-232 module, solid-state relay, and motor driver. And on this slide, it's like the actual motor that we are actual controller that we are using. As you can see, the main difference from the prototype to the actual one is the relay, because the prototype relay was way over spec and expensive, and we found the better solution. So we use a small one-channel relay. And for the components of Arduino gets the signal from RS-232, which gets it from the PC about what actions to take. Relay is there for the brakes. Motor driver moves the motor. Now this is the pinouts for the Arduino Mega, which I decided to choose. A1 and A2 and A3. A2 is relay, A3 is enable. 5 and 6 are the motor drivers. 23, 26, 29, and 27 are the limit switches. Encoder A and B are in 20 and 21, and TX0, RX0, TX0 1 and RX0 is for the RS-232. And now I'm going to pass to Abdullah for restarter control.
Hi everyone. So this is the schematic for the control box. Here we will get the signals from the PLC. We need to control 2 motors. The output of the PLC is 24 volts, and the current is high for the digital input of Arduino. So we have used a resistor and relay to control 5 volt as the signal input to Arduino. The 5 volt and ground is taken common and connected where needed. The Arduino is programmed to sense the input signal from the PLC and control the motors on the step response of Arduino input. Of the basis of the programming, the signal is sent to the saber-tooth motor controller, but we need an interface circuit in addition to limit switches as shown in the schematic diagram. With the help of this interface, motors are controlled in directions. Next slide, please. As a system control team, we want to establish a communication between the PLC and the restacker cart. And since the restacker cart is going to be moving around the place, we have to make a wireless communication. The communication between the PLC and the restacker is going to be through HC05 Bluetooth modules. And as you see here, this is the communication hardware architecture. On the left, we have the PLC connected to the master control. And on the right, we have the slave, which is going to be connected in the restacker card. The way it works is once the master control receives a signals from the PLC, it is going to send enable to the slave. Then we will be able to send commands from the master and receive the status of the restacker card. Also, as you see here, we have two types of Arduino, that because we want to separate the enable from the commands. Next slide, please. So here's our test and results. Test 1 shows that we are able to send and receive a wireless signal by pushing a button from the master control, and once the slave receives the signal, the LED will turn on. Test 2 shows that we can send commands to be able to control the restacker card. Next, please. So next, my friend Man is going to conclude our presentation.
In conclusion, I would like to say that our system architecture is complete. The controller is 80% built, intrusion sensors are working properly, and communication with restocking card is working properly. And I would like to send the acknowledgements to Dr. Rad and Professor Ted for helping us out and advising, UPS for sponsoring our project, and our liaison, Isaru Ramirez, for helping us through, and Professor Thornburn and Bachman to help us for any other problems which we had. Thank you.
And thank you. It's a very interesting presentation. Okay. So we have time for questions. Who would like to go first? Be sure and unmute your microphone.
This is Carl. Just kind of a general interest question. So you talked about how the sensors will detect intrusion into the gantry area, or if a package falls off the conveyor or the transporter and doesn't make it into one of the bags. Did you have a requirement, or did you guys think anything further about sort of overall safety? You know, where everything just comes to a complete stop and either recycles or goes to a wait state to see if the hazard is cleared or the person's out of the way, or whatever actions need to happen.
Well, essentially what we wanted to is to completely everything come to a stop when a beam is broken. So what I was able to do was, as soon as the beam was broken, it would turn off. Okay. So if I walked inside the gantry and I broke the beam and I stood there, but then if I walk, let's say, forward and I wasn't getting the X, how would I say it? If I walked past the beam and I was inside the gantry, but I was not in the place where I would be detected by the X, the group of X, the X, then the system will continue going. So if I had a little bit more components at home, I would have been able to probably add the switch in to completely add emergency stop when that happened. But that is essentially what we completely needed to do.
Okay. And what would the startup function look like? I mean, do you have to reset the whole system, or is it simply clear a fault flag and then it starts up again? Or did you get a chance to look at that?
Yeah, I think if, oh, sorry, I didn't mean to interrupt.
Go ahead, Jose.
If we could go back to that one particular slide in the presentation.
This one?
I think it was like really at the beginning. A couple more. There you go. Yeah, so this details our startup and reset mode. And so what we have is whenever we cycle power or we have a fault, right, the first thing we want to do is we want to read that e-stop. And so there is an e-stop as well on the master controller next to the, or it would be on the operator panel, as well as a light that, you know, indicates that the system is running. And so based on this, right, if the e-stop is not pressed, then we do go into a safety check just to make sure that like there are no, there's nothing intruding on anything and that like all the components are good to go. Does that answer your question?
Yeah, exactly what I was looking for.
Oh, okay, right on.
Yeah, nice.
Okay, other questions?
I've got another one. So you talk about the you know, beam connections and having to align beams. Were there any changes, or was that exercise relatively straightforward, or were there geometry situations with the gantry or other attached locations of the beams that you had to either modify or would modify if you know, went forth with a more operational system?
So for the geometry you're saying, can you ask that question one more time, please?
Well, so if you go to that slide where you're showing the gantry with the beam, the blue beams going around, yeah, or the red, excuse me. So is that like a perfect square, and does it stay square?
Has to be. It would have to. So the sensors work in pairs. So they have to, let's say, if you look at the input I03 and I04, those are a sender and receiving sensor, photoelectric sensor.
Mm-hmm.
So they have to be pointed directly at each other. So the way you mount them, it is going to be a little bit difficult if we actually did get the chance to mount them on the gantry.
Mm-hmm.
But it would be a little bit difficult just because it's a little bit of space away, and wherever you mount your holes has to be right in order for the beam to completely align with the other sensor.
Yeah, I guess one of the things I'm driving at is that, are you going to have like a calibration requirement when this thing is installed, or periodically, where you're going to have to go back and make sure that the beams are, you know, within thousandths of an inch or 10,000ths of an inch or something? Probably not that small, but.
To calibrate them.
If I could jump in, I think from what I've seen of like typical like industrial production level systems, they're usually enclosed. So I think this is more of a, like, I guess a stopgap solution, given that this is a development unit, right?
Mm-hmm. Okay. Yeah, just kind of general questions, because I've seen some of these kinds of systems where some have a lot of tolerance, and you can get away with the beams not being perfectly aligned. And they're mostly light detector kind of things. They're not like laser types or anything. And then the other is that sometimes mechanical structures, especially mechanical structures that are fastened together with nuts and bolts, sometimes get out of alignment. And you have to go back and kind of periodically true them up and square them.
Right.
Okay. All right, thank you.
Okay. Well, thank you, team. It was a very interesting presentation. Our next presentation will start at 5:20, so we've got a short break. The next and final presentation for today is the DOE Solar District Cup team. We are very happy to hear that they made finals. It'll be interesting to see what's transpired since then. Nevertheless, so stick around. The presentation will start sharply at 5:20.
I could say one thing to the UPS team. Just want to thank you all for your efforts. If you're still on listening, I appreciate all the hard work you guys have done, and definitely very detailed on your presentation. So thank you.
Thank you.
Thank you.
Thank you.
Thank you, Kurt. It's T. Fox. Appreciate you, sir.
I appreciate you, T.
Okay, well, welcome back.
Okay.
This is the Expo 2020, our first virtual Expo. The next team that will be speaking is the DOE Solar District Cup team. This will be the final presentation today, but we will have presentations from 2 until 6 every day the rest of this week. You can use the same link that you got on to today's presentation to enter any of the presentations later this week. Don't forget when you're done listening to a presentation to look for the evaluation form. It's a Qualtrics survey. I'll post the link on the chat room. If you can't seem to find it and need your own copy, just send me a note and I'll send you a copy of the link. The students value your feedback, as do I. If there are no initial questions, then let me introduce, this is the Solar District Cup team. Take it away. Go ahead, guys.
Yeah, we're just working on the presentation right now.
Okay.
Getting it set up.
I'm sorry, is the presentation on your guys' end?
Yes, we see
It's
the
showing.
presentation.
Sure, okay, thank you. Just wanted to double check.
Okay, it's not showing on my end. Sorry about that. Let's see. Yeah, Kevin, I don't know, for some reason it's not showing on my end.
Do you have more than one screen?
Let's see.
I see it here, so he's broadcasting it.
Okay. Yeah, I'll open up the slides on my part and then I'll get it all ready. Yeah, sorry for
Daniel, do you want to leave the meeting and try joining again?
Yeah, I'll do that instead. So if you guys could bear with me a little bit and I'll get back on it again.
Okay, we'll stand by.
I guess I'll just have the presentation slides on my side, but if that's okay with everyone.
You mean you're just going to have them separate?
Well, like I'll be reading, like I'll be having the slides on my computer because since mine is not showing up, and I'll read it off of there.
Okay.
Okay. All right. Thank you. So, good evening, everyone. Thank you all for coming. My name is Daniel Davlos, and I'm teaming up with Nobab, Brian, Kevin, Gabriel, and Mohammed, as well as with my advisor, Dr. Landsberger. We are doing the Solar District Cup. And yeah, next slide. So the Solar District Cup is an educational competition which is hosted by the Department of Energy. And so it actually helps challenge the students to help design a solar model and energy storage system for a campus or urban district. Next slide. And so here we have the breakdown about each student's roles and responsibility of what they're incorporated. As you can see, when delivering our package, we have a different forms such as the conceptual design, distribution, financial analysis, and development. And in the next slide, it just gives you a little more in-depth overview of the breakdown of each individual deliverable package that we had to send to the competition of Hero X. And next slide, as you can see, one of the district case that we have is Ball State University, which is actually a public research facility located in Muncie, Indiana. Next slide. And as you can see, the main objective for us, for the university, is to help design a solar energy and PV system, which maximizes the energy offset and financial savings over a 20-year period. And as you can see in the images, outlined in red are the areas in which the university allows us to help design the PV system, which are either on the rooftops on campus or the open field, which we'll be having. Next slide. And now I'm going to hand it over to Nobob, who will go over the conceptual design.
Hi, everyone. My name is Nobob, and I'm in charge of the conceptual system design. Today, I'll be giving you a summary of our PV system performance and site layout. Next slide, please. So we've designed a large 3.5 megawatt ground mount PV system in the plot of land north of Ball State University. This site layout, which was modeled in Aurora Solar software, shows all of our solar panels, inverters, a transformer, and our chosen battery, the Tesla Megapack. Amongst the countless simulations we performed this semester, this 3.5 megawatt PV system yielded the greatest energy offset and financial savings. Next slide, please. The PV module we decided to use for our design is a 330 watt polycrystalline solar panel manufactured by Axitec. It has an efficiency rating of 17%, and using these panels, our calculated system price per watt is $1.71. We made several other module considerations, but the Axitec modules proved to be more cost-effective. Our selected inverter was a string inverter rated for 15 kilowatts and manufactured by SMA Solar Technology. Next slide, please. Here's a summary of our site characteristics. We're installing 10,500 Axitec modules in a 7.5 acre area with a fixed panel tilt of 22 degrees. And the panels were laid out 48 inches apart so that shading from the next row would not be an issue, and thus power optimizers were not required. This is also why only 56% of the area of land is utilized for our solar panels. We wanted to ensure the best solar panel efficiency and avoid shading issues. Next slide, please. Here's our system single line diagram. We have a total of 208 string inverters, which will have its own subarray. And each subarray will have a maximum of 13 and a minimum of 4 modules per string. Conduits will branch out from each inverter and be embedded in the soil, leading to the main distribution line to provide solar power to Ball State. Next slide, please. Here's a block diagram of our PV system. We have our panels connected to a fuse disconnect, leading to the inverter and ultimately to the main AC panel downstream in the university-owned substation. We also show the Tesla Megapack, which is an impressive 3 megawatt lithium-ion battery storage unit. Next slide, please. And this is a summary of our simulation results. So for the purposes of this simulation and for comparison, we decided to use the energy consumption data for the Neuer complex, which is a housing facility at Ball State University. Our PV system yields an annual production of more than 4 million kilowatt hours, resulting in a 67% annual energy offset. We'll discuss in our financial analysis section just how much savings this has generated from this installation. Next slide, please. And so here's an hourly load profile for the Neuer complex for the year. Peak energy consumption occurs around 2 to 3 p.m. for them, and reducing the energy consumption during these peak times and using the energy produced from our PV system will yield the greatest financial savings for Ball State University due to the way their monthly bills are calculated, where we'll discuss that more in a bit. Furthermore, with the introduction of the Tesla Megapack, we can implement a peak shaving strategy, and we set a threshold of 900 kilowatts for the Neuer complex. And whenever the hourly consumption goes above that threshold, the battery will provide the rest of the power. Next slide, please. Finally, here's the specs for our battery storage unit, the Tesla Megapack. We've made several other considerations for our battery, as you can see on the other three choices. But for our system, we only need one single, but the Megapack was the best one for us. And for our system, we only need one single Megapack unit, which has a usable capacity of 3 megawatt hours. It also has a 90% efficiency rating and 100% depth of discharge. Next slide, please. And one of the benefits with the Megapack is that it requires 40% less space than a typical battery storage unit of this size, and 10 times fewer parts. So this modular system can be installed cheaper and faster than current systems. Going off of the peak shaving approach I mentioned earlier, the Megapack can discharge at times of peak capacity to reduce the peak loads and demands on the distribution infrastructure. And now I'll be handing it over to my teammates, Kevin and Gabriel, who will provide a summary of the distribution system impact.
Thank you, Nobab. So the distribution system simulation and analysis were tools that provided us useful information to attempt designing and operating the distribution systems. The common distribution use cases that we tried to take advantage of were peak load management, impact of distributed generation storage, evaluation of distribution and automation design, design of protection and schematics, estimation, operation, and maintenance costs. Next slide, please. So talking about overvoltage, by researching this, we knew that overvoltage occurs when the supply voltage rises above the rated voltage of the equipment or motor. The overvoltage can cause excessive current to flow as well as creating excessive voltage stresses. So we try to mimic or simulate a possible case such as that to our design. We try to use different software applications such as MATLAB, for example. So we try to use a MATLAB toolbox that communicates with OpenDSS, hoping it would make it simpler, but we couldn't get it to fully function, unfortunately. So we mainly focus on just using OpenDSS, and this software was actually recommended to us by the competition. So I'm actually gonna pass it off to Kevin, who will further explain this situation.
Thank you, Gabriel. So as mentioned, OpenDSS is a software simulation tool which allows us to evaluate what's going on within the distribution network. For this portion of the project, our goal was to use OpenDSS to model the PV and storage system which was designed earlier. In order to do this, we had to run the base case. We needed to run the base case that was provided by BSU or Ball State University and obtain the base data. Next, we would modify the code by adding voltage and thermal limits to then slowly code the PV system. Once that was done, we ran the simulate. Once that was done, we ran and compared the base case to analyze any thermal or voltage issues. This would have to be repeated for the PV inverter case and storage model case. However, if there are any violations, we would have to identify a solution in order to resolve these issues. Prior to beginning, we needed to extend the distribution network. So therefore, new lines were added into the existing system that would extend from West Bessel Avenue to Tilton Avenue. Afterwards, the PV parameters were incorporated into the software, which are shown on the left image. However, after running our initial PV case, we ran into issues and spent time attempting to find a solution in order to get the simulation to run correctly. However, with the limited resources that we had with the program, we weren't able to successfully run the simulation properly to obtain the results we had hoped for. I'll be passing it on to Brian with this financial analysis.
Thank you, Kevin. For the financial analysis of our project, we first took a deep dive into how much the school is being charged for the electricity usage and calculated their monthly bill from the data given to us. Next slide, please. The university is billed by Indiana and Michigan utility company based on the gross meter readings and peak demand events at this substation. As bulk purchasers of the electricity, they are charged a base rate derived from 1 minute 15 block of time during the month with the most extensive electrical usage. The peak usage expressed in kilovolt amps is multiplied by $14.72 to determine their base rate for the month. Then their total month's usage in kilowatt hours is multiplied by 1.088 cents per kilowatt hour and added to their base rate to determine their final bill for the month. Their greatest financial savings comes from reducing peak usage. Next slide, please. As Nobab mentioned, we focused our project on the Neuer residential building. Here's their monthly energy bill for the year. As you can see, the months of January and December are the most expensive months for them. January alone is over $52,000. We believe this is due to the heater being on, as Indiana gets very cold during these months. Next slide, please. For our project, one of the competition rules was that we had to use a PPA for our financial analysis. What is a PPA? A PPA is basically a way for the school to fund the project without paying anything. It stands for Power Purchase Agreement. Basically, it's a form of a loan where a developer designs, permits, finances, and builds a system for the landowners, which is the BSU, Ball State University in this case. And in return, BSU, the developer sells the power back to the landowner from the system that produces at a cheaper rate than what they get charged with from the Indiana utility company. And they pay this off in a 20-year period. Our final cost estimate we calculated are shown below. Next slide, please. We were able to lower BSU's annual electricity bill for the Neuer building by over $430,000. This yields almost $9 million over a 20-year period. We got our total cost down to a little under $6 million, and with a 3.5 megawatt system, again, that is $1.71 per watt. In order to pay this system in exactly 20 years, or a little bit less, the project and have the project be financially worthwhile, we calculated that BSU would need to negotiate a rate of 7.4 cents per kilowatt hour for their power purchase agreement. With government grants and other tax incentives, our savings are even greater. Next slide, please. These are a detailed breakdown of what our panels, inverters, Tesla batteries, installation labor, land permitting, and other miscellaneous items. As you can see, eligible government incentives were $1.3 million. In Indiana, for big residential solar PV systems, a state incentive is they don't get charged sales tax on any of the equipment, so that helped a lot. And as you can see, there's some more data there. Next slide, please. With our system in place, here's an estimation of what BSU's electricity bill would look after our system is installed for the Neuer building. As you can see, there are huge savings for January alone, going down from $52,000 to a little over $2,000 for that month. April, they didn't even have a bill at all because our system actually covered all their needs. Next slide, please. Finally, here are some more data we got from our analysis. We used a software called System Advisor Model, short for SAM, to compare our calculations. And as you can see, we were pretty spot on as the model spit out an initial cost of $6 million, which matched our calculations. Now I'll pass it on to Mo for the development and construction plan.
Thank you, Brian. For the development plan, we are going to use the available space north of the campus. Based on our research, we found that the land is a suitable place to install PV system. The land is 7.55 acres, which makes it perfect space to install 10,500 solar panels. For the land use, the total land of interest is 7.55 acres, and the direct land for the development of the PV system is 4.26 acres. The land use is 56.4%. So as my friend Nobab mentioned, our PV system is 3.5 megawatts. Next slide. For the zoning is supposed to be residential zone. The land is an open, stable, and attractive for development. Our PV system will be generating a huge energy to the university. And now I'll be handing it to my friend Daniel.
Thank you, Mohammed. So in conclusion, you can actually see that we successfully designed a 3.5 megawatt PV system. By incorporating the Tesla Megapack, we're able to actually meet those competition requirements, as well as we were able to help the Ball State University to have a financial savings within the 20 years period. And because of the success that we have, Cal State Lake was actually ranked one of the finalists inside the Solar District Cup competition. And another thing that we want to showcase for you guys is, even though it's beyond the scope of our project or senior design, we did like this community service project that our advisor, Dr. Landsberger, has told us about. So Kevin, if you may. So the project that we did is called the Solar Home Model Project. And what it is that it's supposed to give us the hands-on opportunity to build like a miniature PV system, as well as to give us like a better understanding and foundation of how our PV system, how it's going to work. So as you can see here on the picture, you can see that there's a polyhedron structure mounted with two 100-watt 12-volt solar panels, which is going to contribute the power into our system. Next slide. So as you can see here, the PV within the panels will go through like a charge controller. From there, the charge controller will be able to meter out into the batteries, which are parallel in series. And these batteries will be able to give energy through inside the inverter. And with the inverter, we'll be able to incorporate household appliances, which will portray as our load to our PV system. Next slide. So as a result of using the 600-watt hairdryer, we can see that it actually dropped our voltage level below 13 volts. It actually marked up the current from the controller due to the voltage drop. And this reading gave us about like somewhere between 510 to 520 watts. Next slide. So when we turned the dryer off, we just realized that it dropped the power from the inverter, and the voltage actually came back up, which was recovered from the battery bank from the heavy load. And because of the power that was heavily charged to the controller, it was able to compensate from the loss that we had and return it back to its original state. Thank you so much for you guys listening to our presentation. Do you guys have any questions?
Okay, thank you, team. We have as much time for questions as people want to stick around. So who would like to go first? Be sure and unmute your microphone.
I got a couple questions. This is Ted.
Go ahead.
Did you guys have any project requirements on the Ball State power system? And when I say requirements, like, you know, the maximum surface area you could possibly use, the operation temperatures that the system would have to survive, how long it had to live, the lifetime, that affects a lot of things, what kind of voltages it had to provide. So did they give you some kind of requirements for the project that you had to kind of fit within, and did you have to meet those requirements, or did you meet those requirements?
Hi, this is Nobob. Yes, so they did. The competition and Ball State University provided us a document which had all the requirements that they wanted. They provided for us information regarding their distribution system, which we, and they also provided for us a template for their distribution network, which we incorporate into a software called OpenDSS. Not only that, they allocated land for us that they would like us to do some PV design. And they did mention to us that they have this plot of land north of campus in which students are encouraged to design a large ground mount system. We took several different approaches. We tried some of their rooftop areas. We tried the ground mount system as well. And ultimately, our ground mount system yielded the greatest the greatest savings for the school. So yeah, they did have a bunch of requirements in the document they provided for us, and we did our best to address those. And thankfully, you know, and also we're very proud to mention, we already mentioned this, we made it as finalists in this competition. We actually presented last week. I think I was on Sunday. And then, you know, they thanked us. We were very proud to be part of this educational experience.
Okay, I got a couple more questions. So we chose to use the field, the real estate in the field, as opposed to, say, rooftops or overhead parking structures. And why not use rooftops on the buildings? Because that's already wasted real estate space, so to speak, as opposed to use up new ground. And it brings the power closer to where you're using it.
That is true, but for the building that we were looking at, the building in question, they actually did not have, they had a lot of, how do I, there was a lot of air conditioning units on their rooftops. Like their rooftop real estate was not, you know, it did not meet the needs for the consumption of the building that we were looking at. And so we opted for the ground mount system. And we also thought that it would be a much more interesting approach to design.
Oh, okay, okay. You chose an angle of 22 degrees for your solar panels. What was that based on?
Okay, so we use a software called Aurora Solar. And in that software, it produces our simulations for us once we do the PV system model. And so I'm checking up on our performance summary table. Okay, so it gave us, so the way the software gives us results is that it calculates for us our monthly production, and it gives us our energy offset percentage. But not only that, it gives us performance values. So there's a percentage of loss that can be in the system. So depending on how we design our system, we can have a, so let's say we had the tilt at 40 degrees. We had a 16% loss in performance. And then compared to with our 22-degree tilt, we only had a 1.4% loss in our system, PV system performance. So we were just doing a bunch of experimentation and to see what would be best. And we also spaced out the panels far enough so that, you know, like we can't put the panels, you know, completely side by side and use up the entire land filled with just the panels, because there's also requirements and clearances that we have to meet as well for installation.
So what season is that optimized for? Is that optimized for summer or for winter?
This is for year round. So this is for annual. So because there's no tracking system with these PV panels, it would actually make the system cost much more expensive if we added some tracking so that the panels tilt depending on the season. And so that's why 22 degrees tilt is what we had to go for, because they're going to be fixed. These modules are going to be fixed.
So you're assuming the percentage performance every month of the year, but in January through March, we get huge snow loads in Indiana, big snow drifts, and they'd probably cover up those panels. How do you deal with that?
That's correct. So we did look into Ball State's weather and also, sorry, give me one moment. Okay, so in our reports, we have actually a lot more that went into the project, such as shading analysis, battery charge and discharge cycle, and lots of Excel forms that we didn't really show here. But the panels are going to be on like a ballast, so it's going to be pole mounted. So you're going to have a single pole and it's going to be about 4 feet from the ground. And so if it snows, the snow is not going to get in the way of the panels. These Axitec modules that we selected are able to do that. They're able to be lifted up.
Yeah, 22 degrees seems like it's a little bit like a rooftop, and the rooftop gets snow loads build up on it. I mean, we're putting in panels down by the equator, and we're at 23 degrees, averaging over all the seasons. And when I was at Purdue, we had solar panels, but they were really canted, steep, not only to keep the snow off, but because the sun was so far down on the horizon, mid-seasons. The winter it's really low, and because Indiana's pretty far north. So the numbers seem a little, that seems a little optimistic to me, but it's based on your simulation, so I guess we go with it. I had just one more question. You have the Tesla battery packs, and in your slide it says you take them all the way down to 100% depth of discharge, and I assume those are lithium-ion batteries, but how long can those batteries live when you completely deplete them? when you take them down to 100%? That means there's zero state of charge. That means they're completely flat.
So there's actually a warranty for the Tesla Megapack batteries. That warranty is for 10 years, and our analysis is within a 20-year period. And so we took into account in our financial analysis as well, equipment replacement costs. And even with those considerations, and not only that, this Megapack is actually just one single battery storage unit, which is, it's large, but it reduces the monthly bill for Ball State University.
Yeah, the question's on depth of discharge. How far can you get down a lithium-ion battery before?
It's a 10-year warranty. Sorry.
The question's on lithium-ion battery. I assume those are lithium-ion batteries, but can you really discharge them 100% every day?
That's what Tesla is
I think they're going to last less than a couple weeks.
That is what Tesla's claiming from their website. We're just using their data on the batteries. It might be exaggerated in their advertisement, but that's just what we used. Also, regarding your 22 degrees question, Bob made this clear. From our simulation, we have to put in our location of the university, and that's where we kind of got that degrees tilt angle degree from. It just averaged us from their seasoning and from their weather. In the software, they spit out a certain number of degrees, and we just experimented a lot with it. And regarding the snow buildup, I added in my financial report a little extra maintenance costs wise, just for that reason. If when it comes winter time, they got to get the snow off the solar panels, they would.
Oh. So somebody go over there and probably brush them off. Yeah, the battery numbers sound very fishy. I've just never heard of a battery system that we could take down. In fact, very conservatively, the power systems we put in down in Mexico, we only take those down 20%, and we get about 5 years life out of the batteries at 20% depth of discharge. So 100%, we'd probably destroy the batteries in a few weeks. In fact, we actually have. We have destroyed 30 batteries because they're allowed to get down flat. So that number's a little suspicious to me, but again, maybe there's more to the story, and maybe you're not really discharging the batteries 100%. You're taking 100% of the available power that Tesla is allowing you to use, and they're still allowing that battery to be charged up 70%, but they just don't tell you. Kind of like how your cell phone works. When your battery goes dead, it doesn't really go dead.
Ted, this is Sam in speaking. Yeah. Two things. One, I don't know if you're using lithium ion. They're designed, of course, for very deep discharge compared to a lead acid or a glass matrix type. That's obviously a very distinctive aspect of them, or they couldn't be used in electric vehicles. They're protected about 10 times over against over discharge. So when they say 100% discharge, that's probably going between 80% and 20% of full capacity. They simply don't let you over discharge those things like you could with, say, a lead acid or something. And I think that on the question of the 22-degree panel, I think woven into the assessment that their Aurora software gives them is the fact that they're trying to make optimum use of a given fixed amount of space with panels. So of course, if you tune it to the latitude, you get a much steeper panel inclination, but then obviously you then have to space the panels much further apart. So you play a game of optimization between how close you space them and increase the number of panels, and how steep you have them and get the most out of each panel. And I think that's where the 22 degrees comes out, as that balance between making optimal use of a given amount of acreage and getting the most out of each panel. That's my guess is what that optimization scheme is doing.
I see. Okay, very good. That's it for me.
Okay, other questions?
I had a question. You mentioned for the power purchase agreement that Ball State University would be purchasing the power at 7 cents a kilowatt hour. Was that right?
7.4 cents.
So, but don't they buy it from the grid at 1 cent or 2 cents?
That's after their base charge. So
Got
they,
you. So what's like their, what would they pay on average? I was trying to think.
I don't know the exact total. I can, if we can go
Okay.
back to the slide.
But it's more than 7 cents, I'm guessing?
Correct. Yes, yeah. way
Okay,
more.
cool. I was kind of curious. So did you guys try doing different, because I was thinking the first thing you do is like, hey, how many megawatts of solar panels do we think we want to use here? Did you try using different like overall size, like power capacity for the panels to see which one was the best in terms of cost? Or did you kind of stick with the 3.5 just to fill the space and then kind of see the costs after that? Because so I couldn't tell if you had some, different, if you considered some different sizes, or if you just kind of filled it and kind of said, let's see what we can do with that.
We did. We went and looked at SunPower. They're a company for solar panels. They had a bunch of cases for a bunch of universities, including San Jose and Long Beach and some other Arizona state, I think. And we took a look at how much their overall cost was and how many panels they installed on given the land space that they used it on, and then compared what their offset was for the energy usage. And then I think Nobob can answer some more regarding that as well.
Yeah, so we did look at several modules, PV modules. And the two main ones that we came down to was the one that we used, Axatech, and the other one, like Brian mentioned, the SunPower Core panel. But then the main difference between those two panels was that
I was thinking more about the you chose like 3.5 megawatts, and then with battery, I was thinking, could you go maybe 2 megawatts, and then you wouldn't need the batteries, and so maybe it would make out on a per kilowatt hour, you make out pretty good, maybe. So I was just wondering, is there some play around you could do with that?
So yeah, that is true. But the reason why we did include this battery is because it was a requirement by the competition. They wanted us to, incorporate energy storage and learn about it as well. So our approach was, because we only have a 67% energy offset, we're not completely, we're not producing the same amount of power that this building is consuming. And so our approach was to just reduce their monthly bills, and the battery storage will help do some peak shaving. So let's say on any given day, they're consuming, let's say 1,500 kilowatts. So the way their monthly bills are calculated is that they take the highest peak value that was generated within a 15-minute interval, and then they multiply it by $14. So if any 15-minute interval in that day, let's say it was the peak value was like 1,500 kilowatts, they're going to charge 1,500 times $14.76, and then add that to the base rate. And let's say we during 2 to 3 p.m. is their peak times, and we kick in the battery storage during that time to reduce the peak load. Their monthly energy bill will be much lower. And so that was our approach that we took. As for more information on the battery, Tesla's Powerwall is very commercially viable, and then the Megapack is a less known battery storage unit, but it's very powerful. And we did actually try to approach them with our questions, but then due to the recent events, they actually haven't even gotten back to us. So we tried to do our best, to create a nice PV system with energy storage.
Chris, we also use the batteries. Dr. Landsberger actually gave us an idea where since they get charged on their peak kilowatt hour usage, we thought we can store some electricity from the utility company at night when the peaks are a lot lower, and we can store the batteries that way, and then we can compensate off their energy usage and their bill.
Yeah, it's cool. It's really interesting to see the way they purchase power, and see some of the strategies you guys implemented. Well, that was very cool. So I like how you guys took a lot of different strategies and the really kind of different aspects of the project. So
Thanks so
Yeah,
much.
nice job, and then going the extra mile to go and present. I think that was really cool.
Thank you.
Thank you.
Good job. Nice work.
Okay, are there any other questions? Okay, well, thank you, team. It was a very interesting presentation. This concludes our presentations for today, but come back tomorrow, 2 o'clock, or any day this week between 2 and 6. We've got 4 more days, 24 more presentations to go. Okay.
All right.
Don't forget to use the Qualtrics survey and offer some feedback to us. We certainly appreciate that.
Thanks, everybody. And thanks to the students. They did an amazing job, given that they couldn't even get together personally to conduct all this teamwork for the crunch time. So I think they did an amazing job.
Yeah. Good job, everyone.
Thank you.
Thank you, guys.
Thanks,
Thanks, Mike.
everybody.
See you guys tomorrow.
Bye.
Thanks, all of you.
Tomorrow.
Thanks, all of you. Bye-bye.
Bye-bye.
So Gabriel, when do you hear back if you won or not?
We already actually know the results, and for our actual case, we